Okay, welcome everybody. Thank you for coming out early on the Friday morning. It's always a bit hard. It's a pleasure to welcome you at this EGU Union Symposium on mountain building, volcanism, climate and biodiversity in the Andes, celebrating 250 years of after Alexander von Humboldt's birthday. My name is Peter van der Beek. My co-conveners are Mike Burton, Juliana Panieri, and Lily Pereg. We are the division presidents for different divisions in the EGU. So geomorphology for myself, geochemistry, mineralogy, petrology, volcanology for Mike Burton, biogeosciences for Juliana, and the soil sciences division for Lily. Very unfortunately, only 3 of us can be here today. Lily Pereg died under tragic circumstances earlier this year while she was in Argentina. She was extremely enthusiastic about this symposium, and she is with us in our thoughts and our minds today. So we have 6 outstanding talks lined up. They are scheduled for 30 minutes. We have actually a little bit more time in the time blocks because we have 1 hour and 45 minutes for each time block. So there will be some time for discussion at the end. And I would just like to give you a very brief word of introduction on Alexander von Humboldt and why we are celebrating him and why he is so important for a large number of communities in the earth sciences. Alexander von Humboldt was really a great explorer and an extremely well-known scientist at his time. His book series, The Cosmos, which he published in the mid-1900s, in the mid-1800s, in the mid-19th century, was published in numerous languages and was really a worldwide bestseller at the time. He was many things. He started out as a mining engineer, but made major contributions to many fields, including biology, botany, geography, geology, geophysics, meteorology, etc. And he was one of the first to really express a holistic view of science, and in that way, he can really be seen as the precursor of what we now call Earth system science, by placing links between geology, topography, climate, and biology. And he traveled extensively, and his most famous journey was to the Americas from 1799 to 1804. You can just see the map here, and that's really what the part of his life that we're lifting out here, his contribution to the Andes and to the knowledge of Northern South America. While there in 1801 and 1802, traveling between what is now Colombia and Ecuador, he climbed a great number of volcanoes, and while doing that, while changing altitude, noticed the organization of the vegetation, of the plant life, and for the first time expressed this idea of altitudinal ranges of plants, and also the interactions between plant life, the biology, the climate, the soils, and the underlying geology. And he expressed this idea also in quite a revolutionary way for science communication in the Naturgemälde, the nature painting that he published a few years after coming back, which was really, I think, the first scientific poster, where instead of describing everything, he meticulously drew this out and then described all the relationships in this very famous scientific contribution. And finally, one other thing I would like to point out, which I think is quite remarkable, is this quote from 1800 while traveling in Venezuela, in what is now Venezuela, and seeing what the settlers, the colonists were doing to begin agriculture, and what he wrote in in a letter and later published is this quote: "When forests are destroyed, as they are everywhere in America by the European planters with an imprudent precipitation, the springs are entirely dried up or become less abundant. The beds of the rivers remaining dry during a part of the year are converted into torrents whenever great rains fall on the heights. The sward and moss disappearing from the brushwood on the sides of the mountains, the waters falling in rain are no longer impeded in their course, and instead of slowly augmenting the level of the rivers by progressive filtrations, they furrow during heavy showers the sides of the hills, bear down the loose soil, and form those sudden inundations that devastate the country." So I had completely understood the links between vegetation, deforestation, precipitation, hydrology, erosion, and he was warning against human intervention in nature. And this was at a time of the thinking of progress, where nature was something wild and bad that had to be tamed by man. And so this was really, again, quite revolutionary and quite a precursor to the way we think about these problems nowadays. Okay, I won't say more than that now. I think several of the speakers will come back to some of these points. And so we have 3 talks in the first half of the session until the coffee break. And the first speaker is Manfred Strecker. And Manfred holds the chair of general geology at the University of Potsdam. He has a PhD from Cornell and has been assistant professor at the University of Karlsruhe, as well as visiting professor at Stanford and Cornell universities. He obtained the Leibniz Prize from the DFG in 2004. He's an honorary fellow of the Geological Society of America and a member of the Leopoldina Academy of Sciences, for whom he is actually also organizing a Humboldt symposium that will take place in June. Manfred studies, amongst others, the relations between climate and tectonics and their influence on erosion and sedimentation patterns in time and space. He has worked extensively in the central Andes of northwest Argentina over the last 30 years or so, and he will talk to us about Alexander von Humboldt's legacy in current Earth system science research in the Andes.
Yes, good morning, and thank you very much, Peter, for those kind introductory words, and thanks to the organizers to organize this very interesting set of talks for this morning. Now, here is Alexander von Humboldt, probably in his early 30s or early 40s in the beginning of the 19th century, and I guess that was the only time when being from Prussia was a cool thing. So because he left Prussia with money from the Prussian king and went to Paris and lived there for almost 20 years. And a lot of his seminal work was done while he was in Paris. And a lot of it was discussed and a lot of ideas were generated at these soirees that they had with Cuvier, the whalebone guy, and among other things they discussed the newest Scottish literature. Quentin Durward was discussed over there, but then also when Charles Lyell came to these meetings, they started discussing the importance of isotherms for geological research. And this is a little bit the direction that I want to take. Peter mentioned a lot of the different aspects that Humboldt touched upon in his different publications. And I will mainly concentrate on the issue of climate, tectonics, and topography, and we'll view that early work of his also in the context of the things that we're doing now with different methodologies, with different technologies, and then still make a point that this early work was seminal and this early work was very important, and it has taught us basically to think across our different disciplines and go away from those isolationist research silos that we're typically in, and that we spend more time talking to our colleagues from other fields. So everything is connected, and we will see how connected some of these things are. And I have cast my talk into 4 different parts. First, I would like to talk about Humboldt's contributions to climatology and how those ideas that he had were picked up by others and made them useful for the field of geology. And then I will spend the bulk of my talk on the recent climate characteristics and the way the South American climate in the southern central Andes developed over time and what kind of impact that has had on erosional processes and sediment transport processes. So those are the different fields, and what I will start out with is with this picture by Frederick Church. He was a second generation Hudson School painter who had very close relationships with Humboldt. They were writing to each other, and Church read Humboldt's books and also looked at his different sketches from Ecuador, and that prompted then Church to travel to these areas and come up with this beautiful landscape picture of the Andes, the heart of the Andes. It doesn't exist, this landscape here. It's a composite of many landscape paintings and sketches that were done by him and by Humboldt. But I guess there's a little bit in there for everybody in the field of geosciences, from the geobotany all to the vertical zonation of plants, the snow lines in high mountain areas, mass movements, the role of faults and the generation of knit points even. And so there are different things that we find here in this picture that teach us more about this kind of thinking of the environment that Humboldt developed and that many of his admirers followed upon. Now, but one of the biggest contributions of Humboldt, I think, was his contribution in climatology. And it's not that I came up with this idea, that's what many people think, of course. And what we see here is the way climate data was recorded in those days when Humboldt started recording precipitation, temperatures, and whatnot. And this was the computational style at the time, but nobody could do anything with these figures when it came to expanding these observations to a larger region, a country, a continent, or even worldwide comparisons. And it is basically Humboldt who came up with the principle of the isotherms, the lines of equal temperature that he connected, and where he actually recognized that instead of being parallel and equal in width, that these isotherms are not at all equally distributed around the globe. And he concluded that elevation has a big impact on their distribution, but also not just elevation, as we see down in here, but also the position of the continents with respect to the oceans and the distribution of land mass versus oceans. And this then ended up in this beautiful map that was published later in 1838 after Humboldt's earlier writings. And this was taken by Charles Lyell as a possibility to introduce this concept into geology. And it was about the time when Lyell was just about to write his 3 volumes of the Principles of Geology, where he then used the principle of the isotherms to use them to explain the distribution of land and oceans. He used it in order to explain the Humboldt, not the Humboldt current, but the the Gulf current in the Atlantic, and it's actually surprising when you read volume 1 of Lyell's book how much he actually used this data that Humboldt provided and how he then introduced it into the field of geology. And he wrote to his friend, who was also his editor, so to speak, in present-day language, my dear Scrope, he wrote that basically the geological application of all of this is mine. And not only did he look at the distribution of land and water, he also looked at the role of mountains in cooling down the temperature of the Earth. And there's pages and pages where he looks at the influence of high topography in high latitudes versus low latitudes, but also the role of vegetation and the role of the distribution of oceans and land masses. So that's quite amazing, and it's written all in there. This is prior to the publication of his book. Now here we see something that followed then these early writings of Humboldt, and Humboldt called it the comparative orology. And that's basically a term that would describe the study of surface processes in high mountains in relation to tectonics, in relation to the buildup of topography, but also with respect to the vegetation cover, as Peter pointed out before. That was an important issue, the linkage between these different aspects and landscape evolution. And what we see here is this comparative representation of snow lines in high mountains that then also led to a better understanding of the distribution of precipitation and temperatures in high mountains. And in comparison to this picture that you saw before, in this comparative rendition of mountain ranges in different areas, here we have the Andes, here the Himalaya, you can see that this is much more realistic than the earlier work in 1807, when the snow lines and all these other lines were still horizontal. And here we can see the asymmetry that is so typical for many mountain ranges. But what I would like to point out here is many people consider Humboldt the father of plant geography, of geobotany, and I would like to start at that point because he came up with this map here. This is from an atlas where he shows the distribution of plants worldwide. And there's one plant family, one kingdom, according to him, that stretches the eastern part of the Andes in Peru, Bolivia, and northwestern Argentina. And this is the monsoonal dominated or influenced forest that we call the yungas, which is comprised of plants that do very well in areas with high precipitation, but that also can withstand seasonal drought. And this is where we go into the present-day climate of South America. And before we do that, let's have a look at the distribution of rainfall in South America and other areas at similar latitudes in the Southern Hemisphere. In all of these areas, we have deserts at these latitudes at around 20 to 30 degrees south. There are cold ocean currents in front of these continental margins. And all of these areas are arid or even hyper-arid. But when we look, there's a big exception here at this area in the eastern slopes of the Andes, because here we have high precipitation. And why is that? And why don't we have these kinds of features in these other areas? Well, the answer for that is it is topography. Here we see the north-south representation of rainfall and topography on the western slopes of the Andes, basically along the western slopes of the Andes from north to south. And in the next slide, we see that similar area, that same area actually, on the eastern slopes of the Andes. And we can see that these areas are characterized by high amounts of rainfall, 2,000 to almost 6,000 meters of rainfall on the eastern slopes. So topography plays a big role. And this is something that was recognized early on. And in fact, this is basically the picture that we're seeing today with the South American monsoon, where moisture is being routed from the Amazon basin along the Andes all the way into northwestern Argentina by the low-level Andean jet. And this low-level Andean jet curves around in a very strange way down in here. That's not an artifact, but this is most likely the reaction to air pressure changes that are brought about by the high topography in the southern part of the Altiplano Puna Plateau that heats up in the summer and that then attracts this moisture that is being funneled along the Andes down into these areas. And that creates these very pronounced precipitation gradients in that area, and that has a very fundamental impact on the overall distribution of rainfall, on the amount of rainfall, but then also on the surface processes that are a function of this topography, the slopes, and the amount of rainfall, and the style, how this rainfall is actually brought to these areas. But when did this all begin? And I'm coming to my next point, and I'm starting out here with a very nice little modeling study that was done by Kerry Cook and John Lenters already some time ago. And what they do is they show topography in South America on the order of 100 meters. And then they look at the potential distribution of rainfall. And it looks like this, which would leave the southern central Andes, the area that we will be looking at here, in a more arid environment than it is today. If they introduce a threshold elevation of 1,500 meters in this environment, and all of the areas that are above 1,500 meters are shown here in the gray, then we get major changes in the system. And why did they use the 1,500 meter contour in areas beyond that? They used it because this is the area where basically 80 to 90% of the precipitation in this environment falls today. And this is the modeled precipitation distribution that we get from this area, which would look very similar to what we're actually recording based on instruments. Now, but when did this all begin? One possibility to study the onset of this kind of climate regime is through the basin deposits in this area that now receives this monsoonal precipitation and is characterized by heavily vegetated mountain slopes. And Carmi will talk about this later on in greater detail, but one possibility to assess the paleovegetation and perhaps the paleo-humidity conditions in these environments is by looking at the stable carbon isotopes, because they reflect through either soil carbonate concretions, rhizoconcretions, or through organic material that is preserved in these soils, a relationship between C12 and C13, the delta C13, which would, in one end member case, basically represent a dry climate, and the other end member case is a wet climate by the C3 plants by increasingly negative delta C13 values. And this is the field view of these features, and we're looking now at one of those deposits in Bolivia, and basically we sampled these kinds of deposits in great detail. And we have several locations where we did these kinds of studies, and I will be talking about this area over here, the Angosto de Pilcomayo. And here is just an example of one of those charts. Basically, all of those black units are overbank deposits of former river systems where we find these paleosols, and where we also are fortunate enough to have the preservation of volcanic ashes that allow us to date these different units. And those are marked, if you can make it out, with these red dots over here. So the next slide already shows the result of one of those sections, and in fact all of those sections look the same. And that's interesting, because what we're seeing is in the very beginning we see an increase, or actually it's a decrease over time in the delta C13 values, which would mean it is getting wetter and wetter. But then here, sometime around 9 million years ago or so, we have the oscillation around a mean. And this different trend here is explained by us as the onset of the monsoonal climate in this area. Now, let's go to another place in Argentina over here, where we also see some interesting issues in these intermontane basins. As you can see here, these are intermontane basins that straddle the margin of the Andean plateau, and it is in these areas that we find sediments that are wedged in between a sequence of alluvial fan deposits that are intercalated with aeolian deposits, and again with alluvial fan deposits that are heavily cemented by carbonate. And the units that I'm talking about are these over here, and these are the older alluvial fan facies, and here are the younger alluvial fan facies. We also see here the orographic barrier in the east and one other barrier here in the west. So it's an intermontane basin bounded by these faults. And in this basin we find this unit over here, which is the Palo Pintado Formation. And the Palo Pintado Formation is quite famous in Argentina. It looks like this. And you already can see that there is a transition always between red and olive-colored units. And these olive-colored units, they're the ones that contain a lot of plant fragments, a lot of pollen, and they stand for a totally different environment in the geological past between about 9 million years and around 5 million years before present. And this Palo Pintado Formation is characterized by hydrophile pteridophytes, angiosperms, but it also includes crocodile bones, and this is the fossil caiman that is found in these basins. And the basin that we're just looking at is located here, and the stratigraphic column is located over here. And the Palo Pintado Formation has this kind of fossil in it, but when we look at other intermontane basins as we go eastward, we can observe that similar kind of facies occur with similar kinds of fossils. Well, let's say their nearest still living neighbors, but these units get younger and younger as we're moving to the east. So that is the successive incorporation of the foreland into the deformation zone that is represented here, and also the successive buildup of orographic barriers that then intercept that moisture that is coming from the east. The present day nearest living relative of this one is in the Pilcomayo, or in the Bermejo Basin, farther to the northeast at an elevation of 300 meters or so. So clearly an indicator of different environmental conditions, similar to what we see also in terms of the plants. I alluded to that already. And here we have plant fossils. They are basically macrofossils. They're leaves, and they're also tree trunks. And in this case, we're talking about acacia trunks that belong to what I mentioned before, to the Yanga forest, because they're nearest living neighbors, so to speak. They are here on the eastern slopes of the Andean blocks over here. That was the region where we have those high precipitation values between 2,000 and 6,000 millimeters. Whereas here in the center of those basins, we only have precipitation values on the order of 200 millimeters or so. So basically, along the eastern flank of the Andean Plateau region, we have different sites that the Argentines have identified over there where these kinds of fossils occur. And we draw in this very fictitious isohyet, and we overlay this area now with the present day precipitation amounts of this area. And we can see that the precipitation is, of course, very high on the eastern flanks. The signal is smeared out a little bit, where we also have greater distribution of topography due to the differential uplift of these units. But then the interior of the origin is very arid, and we're talking about values between 200 millimeters over here to less than 100 millimeters per year in the deeper part of the origin. And so that seems to show that this area, now from the bird's eye view, we were just in this basin over here, that basins within the origin were formerly characterized by conditions that basically characterize the present-day eastern flanks of the Andes over here. And that shows that we are going from contiguous foreland depositional environments to intermontane basins due to the eastward migration of the orographic barriers. And as a result of that, we have the aridification and the loss of fluvial transport capacity. And we can see that this is not just an imagination, because many of those basins up in here in the Puna Plateau, they are basically endorrheic basin. They're internally drained. They have large amounts of sediments, and every sediment that is being generated due to weathering and due to erosional processes in those high mountain ranges, that sediment is actually not reaching the foreland, like in the other parts of the Andes farther north, which shows that this disparate deformation style here is very conducive to developing these kinds of sedimentary and depositional conditions. We also lose, obviously, fluvial transport capacity, because otherwise the interior parts of the origin would have been captured by these rivers that are draining here into the foreland. And that's the last point that I want to make. And first of all, we see our orographic barrier has moved eastward over time, and therefore we may have a situation here on the present-day eastern slopes of the Andean Plateau like it was maybe 5 million years ago over here in this location. So I'm coming to the rainfall gradients now and surface processes, and I have a little bit time left, luckily. We see this very same area that we saw before. These are mountain ranges here that are 5,000 meters high. These over here are on the order of 3,000 meters high, and this prominent feature here is the one that we are seeing here. So you can appreciate this enormous gradient in rainfall, but also an enormous gradient in the vegetation cover, and also the associated surface processes that impact this region. And we studied this area by looking at basin-wide erosion rates, and basically we have these very different environments. On the eastern slopes, we see these kinds of features here. Vegetation, yes, but at the same time, a lot of sediment transport from the higher ranges into the basin. And then in the interior of the origin, we see these highly arid areas over here. We looked at these basin-wide erosion rates using beryllium-10, which helps us to understand the time that sediment was exposed to cosmic rays. In other words, if there is a high concentration of beryllium-10 nuclides that we then collect at a basin outlet over here, then we would assume that the high amount of residence time is also a representation of the low erosion rates, whereas if the concentration of nuclides is low, then this would stand for accelerated erosion rates. And we are seeing that now in a regional distribution, and we can see that these areas with the higher erosion rates all straddle the eastern flanks of the mountain range, and the farther we go into the interior of the origin, the smaller the erosion rates get. And when we look at this in one swath profile here in the southern sector, where you see topography overlain with precipitation, and then on top the basin-wide erosion rates, we see a major decrease from the eastern sectors into the interior part of the origin, basically from 1 millimeter to 0.02 millimeters. So basically 2 orders of magnitude difference in these environments. And this is a true representation of these very pronounced features of asymmetry that are associated with the topography and with the forced precipitation regime that is related to the South American monsoon. Okay, so I guess my conclusion is climate matters, and at the same time, as we have seen, tectonic also matters, topography matters, atmospheric circulation matters, botany matters, and erosion studies are equally important. And this is basically coming back to Humboldt's idea that everything is somehow connected with each other. And I think my only conclusion at this point for this talk is that it is nice to see that in several circles, people are thinking now again in terms of an Earth system science, and that we're going away from this very isolationist thinking from our disciplines. And I think this is something that Humboldt taught us, and that is something we should think about in our future work. And I thank you, and of course, my numerous co-authors who have helped me over the years and whose support I deeply appreciate for your attention. Thank you very much.
There's time for 1 or 2 questions. No, the room is still waking up. Okay. In that case, thank you very much, Manfred. And we'll move on to our second speaker. Gerhard Werner is professor of geochemistry at the University of Göttingen in Germany. He holds a PhD from the Ruhr-Universität Bochum, where he was also an assistant professor after a postdoc at Le Mont Doherty Geological Observatory. He subsequently was an assistant professor at the Universities of Mainz and a Heisenberg Fellow at Le Mont Doherty before becoming full professor in Göttingen. Gerhard Werner obtained the Leibniz Prize from the DFG in 1997, the Hans Stille Medal of the Deutsche Gesellschaft für Geowissenschaften in 2013, and a Distinguished Career Award from the Geological Society of America in 2014. He has worked extensively on magmatism in South and Central America and elsewhere, and was recently a guest editor on an elements volume on the Central Andes. And Gerhard will talk to us about the roots of volcanism in the Andes. Gerhard.
Thank you for the introduction and the invitation to this nice event. As a geochemist and petrologist, I will have to treat you who are not geochemists and petrologists with a number of diagrams and plots and data, but I'll try to be as easy as I can by always explaining the principle and what we draw from these data. My talk will have these 3 major parts. First, I will talk a little bit about Alexander von Humboldt and his role in the discussion and the dispute about the origin of basalt, and Goethe was part of that, and he had a very close relation and discussion about this issue with Goethe. I will talk about the modes of volcanism, what types of volcanism exist in the Central Andes. This is, of course, an area that Humboldt never has visited. His southernmost part of his travel to South America was Lima. But he did have then an appreciation of the Atacama Desert and the dryness in that area. And then I will go to the core, talk about the spatial and temporal compositional variations and the mineral chemistry and what they tell us about how to make an andesite. So I hope I will be leaving you with a recipe how to make andesite in the Andes and probably somewhere else. In more detail then, I will touch the issue of how fast and you can make an andesite and how long is the resident and ascent of these magmas. And there are distinct regimes to make andesites, and I will talk about those as well. Goethe, in his Faust, wrote about Mephisto, who was the devil and who was the Plutonist. And he was farting and stinking and revolting. And then Faust, of course, was the guy who tried to get everything in order, and that was the Neptunist. What was the issue at the time? It was A.G. Werner who said that basalts are simply the result of chemical precipitation from seawater. It is always the youngest, and then you have older rocks below, and granites is the oldest always. Then the volcanists, they realized that by going to Italy, that there is lava flowing out of craters, and they thought that this was because of melting in the crust, and that melting was caused by the burning of coal seams. And then, of course, Lyell and Hutton, they were the Plutonists, and they got it right. They realized that basalts form from crystallizing magmas that rise from large depths. And same as granites, magmatism is the basic process behind formation of basalts and granites. And they can have any age relation, whatever the geology will show us. Goethe, however, remained completely unconvinced. To the end of his life, he hated the idea of revolting basalts coming from below. He also didn't like the French Revolution. He was an obedient server to his superiors. However, he discussed the issue with Alexander von Humboldt, and Humboldt himself was a Neptunist because he went to the Eifel and said, I can see no indication of a volcanic or plutonic origin of basalt because the basalts were interlayered with marine sediments in the Rhenish Massif. So he was convinced that basalts form from chemical precipitation from the ocean. Then he went to the Andes and he saw the volcanoes there. This is the famous Chimborazo that he climbed. And of course, going from the past to the present, the Humboldt still is around in a way, because he realized that it could not be true that these basalts and these lavas formed by precipitation, because what he realized was that there is a large-scale pattern to volcanism. It's not a local issue. It is large structures and huge edifices, and he realized that the source of basalt and the source and the roots of these volcanoes lie deep. And this is what I'm going to be talking about. And he already had the Pacific Ring of Fire on his maps. And when you look to South America, he realized the large and regular spacing of volcanoes, and he came back as a Plutonist. Still, Goethe couldn't be convinced by him. They discussed the issue further, but there was no way that Goethe could be convinced. Today we know that the reason for the spacing of volcanoes and the lines that these volcanoes form not only in the Central Andes and Northern Andes is because of plate subduction. I'm not going to talk about the processes within the mantle that make the magmas in the first place, because the Central Andes is the thickest crust anywhere on Earth where subduction magmatism occurs. I will mostly talk about what the crust does to the magmatism. Now, we've seen part of this map before. There is the dry core of the Atacama Desert and the wet zones of precipitation to the west. And Manfred has just pointed out that a major control on this precipitation pattern is the elevation of the Andes. However, there is another reason, and when you go back to Alexander von Humboldt, he realized the role of the cold, what he still called the Peru current, or the cold Peru current, which brings waters from the circum-Pacific, sort of the circum-Antarctic current, and this only started after the plate separation between South America and Antarctica. So there's a link between plate tectonics and climate, and the Peru current, now the Humboldt current, is an excellent example for it. And it brings cold water, and that means cold air to the western side of the Andes, and there is no orographic rain from the west. And this makes the Andes, the Central Andes, special. It's great for studying volcanism because the volcanoes that you can see have all kinds of ages and they're still there. So in the Andes, we can study the interplay between tectonism and volcanism, and the plates and the mountain building. I've mentioned the ocean currents. Of course, tectonism and mountain building gives sedimentation, and if there is no sediment coming from, because the climate is so dry, coming from the continent, then the subduction channel will be barren of sediments, which will change the mechanical processes at the subduction zone, which then increase mountain building. So there's a loop across here and back. We talked about desertification and the extremely dry Atacama Desert. We've heard the other day, Earth at a Dry Limit is a large program in Germany that looks at the biological consequences and consequences or links between geomorphology and biological evolution in the Atacama Desert. Climate, of course, drives erosion, and that again connects to tectonic and morphology and landscape evolution. And my take on this is, if you have volcanism and mountain building, then the magmas, their sources and the roots of these volcanoes will change through time. So let's look at the volcanoes. This is the central part of the Central Andes. Peru here, this is the bend in the western coast. You see lots of volcanoes and two types. These are ignimbrites. These are huge, hundreds of square kilometers of ignimbrites, sometimes up to 900 meters, just 3 layers of ignimbrites. These are huge volumes of magmas that are being produced. And then, of course, there is the stratovolcanoes, and I will talk about those as well, and in particular about these two volcanoes, Tarapacá, Parinacota. You can see they are very close. They're sitting on 70-kilometer thick crust, very close in space, but they have certain things in common and other things are completely different, and we will try to address that issue. This is a map that we produced, and it contains all the volcanic centers that you can see on satellite images here. The active ones are red, and again in these colored patches is the ignimbrites of different age. And when you look at the ages and the colors, it goes from red to orange to green to dark green, and this is the age of the ignimbrites. There is a trend from north to south of younging of those ignimbrites through time, and at the same time you have these volcanoes active. When you look at the simple parameter silica for igneous rocks, and maybe from your introductory classes you know that that is a matter of differentiation, we compiled a large number of analyses from the Central Andes, and you see a very nice bimodal distribution. The lower end is because no basalt can actually make it through the thick crust. It gets stuck, cools, crystallizes, and doesn't make it to the surface. And then as you increase silica, the viscosity increases, and then the lavas become too sticky. They cannot come out. However, if they stay and get heated, they can evolve further, and then they increase in volume and they increase in water content, and they can be erupted as ignimbrites. This is just numbers of samples. If you would scale that to volume, this would be huge. So there would be two very large peaks in the abundance, and this, of course, the blue field is the andesites. I will talk about ignimbrites first. These are these sheets of ignimbrites in the Central Andes. Typically, they erupt from caldera centers, which are quite large, so they have several tens of kilometers in diameter. And when you look through time and space, going from the north to south, and ignore the local smaller ignimbrites, you see that the large volume ignimbrites get younger as you go further south. And the hotspot, if you like, today is around the Salar de Atacama area, which was called the Altiplano Puna Volcanic Complex. We talk about flare-ups, that is pulsed activity of ignimbrites in time, but also in space. So again, the ages from north to south change. And what else changes? Well, the subduction of the Juan Fernandez Ridge sweeps to the south as time goes by. Subduction of a ridge means flat subduction, no volcanism. And as the ridge passes by oblique subduction, you will have steepening of the slab. There is a stereophilic mantle coming into the mantle wedge, causing large amounts of mantle melting. That mantle melt goes into the crust, heats up the crust, mixes with differentiation, mixes with partial melts from the crust, and that is the cause, and if you like, that is the root for these large volcanic eruptions in the form of ignimbrites. So there's a north to south passage of that ridge. Today, as I said, the hotspot is in the region of one hotspot of the Salar de Atacama Basin. This is again is the ignimbrite map. You can see from ambient noise tomography there is a huge anomaly within the crust, in the middle crust, which is interpreted to be, some people say, 20% of partial melt. So the crust is partially molten today in the Central Andes, and this is the source for these ignimbrites. And some of the area is actively moving, so the ground uplift from INSAR tells you that these systems, these large systems, may still be active. This is the image. I'm not so happy always with the geophysicist's view of magma chambers. They make these big red blobs. But as a pathologist, we know that it is not just one big block of magma. It's a region where the crust is weak, and the interpretation is that it is at least partially molten. But it's a huge volume of hot and, again, partially molten crust, which is the source for these ignimbrites. Now, there's a link between the ignimbrite flare-ups and the deformation. This is the deformation pattern, the shortening rate. There are two phases of main phases of shortening, one between 30 and 35, and another one around 10 million years. There is a basal arc magma flux that makes sort of the regular input, but we know from the volumes of ignimbrites through time that there are pulsed, high peak intrusions of material from the mantle into the crust that cause melting and mixing in the crust to make these large volumes of ignimbrites. And for those of you who are interested in the numbers, we scale the magmatic flux to cubic kilometers per million year for 1 kilometer of north-south arc extension. So there's a clear link between the crustal thickening, the tectonics, and the ignimbrite pulses that we see at the surface. And these move from north to south. Again, the older ones are in the north, and the younger ones are in the south. So, first conclusion, the ignimbrite flare-ups follow the passage of the Juan Fernandez Ridge. They are caused by increased mantle melting and involved increasing amounts of crustal material with increasing crustal thickness. As the crust gets thicker, it gets hotter, and ignimbrites become more voluminous and have more component of crust in them. Now let's switch to the andesites. Of course, the andesites are the type of magma that make these beautiful stratovolcanoes in the Andes. This is Paina Cotta, where we have worked for many years. It has had 160,000 years of activity, and it goes from basalt to rhyolite. So it's a very diverse eruptive history for a short time. And just 35, this is it again, so there is the story. So we start at 160 with the base, then we have a rhyolite plateau, then we have from rhyolites to basalts in the old cone, then we have a sector collapse, which will become important. So the entire volcano gravitationally collapsed around 8,000 years, and then it was rebuilt as a young cone, which is the present shape of the volcano. So a very diverse magma composition and a very brief history. When you go to the Topography volcano, it is has 1.5 million years of activity, and it's boring. 1.5 million years, dacite, dacite, dacite. As a petrologist, you may say this is not interesting, but I will show it can be quite interesting. So with these two types of volcanoes in the background, we can ask questions. What is the magma composition and what are the mixing end members? What is the pressure and temperature of crystallization and the mixing? And how long does all this take? So let's look at a simple diagram. The alkalis with the silica. In the background, you see all the data from the Central Andes. Now, this is Paina Cotta, this large range of compositions from basalts to rhyolites. And then Tarapacá, it's clustered around the silicic andesite, and the dark blue dots here are mafic inclusions. You find the dacite, and it has andesite blobs in it, so you immediately see there's magma mixing going on. This is the dacite from Tarapacá volcano, and they give you some clues about the sources of these magmas, because in a very, very simple way, we plot strontium versus silica, and here are sort of the basaltic inclusions, and they have a large range of strontium. No way you can do this by magmatic differentiation. These mafic magmas must come from different sources. These are the light blue ones are the dacite, and when you link each mafic inclusion with each host, this one mixes with this one and trends here, and this one mixes with this one and trends here. And when you do that for all of them, you get an end member. So there is magma mixing going on between different kinds of mafic recharge magmas, and one magma that we call rhyodacite end member, which sits around 68 to 70% silica. So these andesites, dacites are the product of mixing. And we can go to the Central Andes in general, the same data set here. Now, this is all of the Central Andes, and this is from the Southern Andes. We can basically explain, except for these highly differentiated magmas, all of the compositional variation in the Central Andes by the mixing of three end members. Two magmas come from the mantle of different composition, and we can discuss, not here, why they are different and what causes that. And this is mostly a crustal melt that forms in the crust, and then you mix either across here to here or here to here, and then you can explain all of the variation that we can see in the Andes. And again, with the alkalis, the same story. This is the triangle of mixing, and this is the entire data set for the Andes. There's only one volcano that doesn't play the game, and that's Lascar volcano. And apparently, it just simply has a different mixing end member here on the silicic side. So mixing is the main process of making andesite. You take mafic recharge, you take a crustal melt that was formed inside the crust by melting and mixing and differentiation, and then you just mix the three, and you can explain all of the magmas in the Central Andes. And coming back to this histogram, here are the two end members, recharge magmas, resident differentiated magmas. The differentiated magma that is an important mixing end member hardly ever makes it to the surface. It is too viscous, it just sits there, and the only way to get it out is to bring new mafic magma in, mix it, and then you make the andesite in between. You have to reactivate this resident magma. So andesites are the product of magma mixing. Now, temporal changes. How did this work in the past? We've heard that the Andes formed in the last, say, 35 million years. And here we take a ratio of two elements, samarium and terbium, which is an indicator of pressure of magmatic processes. I'm not going into the detail why that is, but now we're going through time from the Jurassic into the Cretaceous, into the Tertiary, and you can see this geochemical signal changes as the crust in the Andes evolves and becomes thicker. As the mountains rise, the crust becomes thicker, and magma processing happens at greater depth. And the big jump is basically between 10 million years and the present. So this is a major change in the trace element signature of the magmas that become erupted, and this reflects the rise of the Andes and the thickening of the crust. That's through time. Now, this is magmatism through space, and for those who don't know about isotopes, don't worry about it. This is lead to a 6:4 ratio. It just is a measure for the time-integrated uranium-lead ratio in your material. So if you change uranium-lead now, it doesn't change the isotopic ratio. If you have changed it hundreds of millions of years ago, then you will get a change. And what happens here is we can find different domains by the colors of these isotopes, and they simply reflect the composition of the continental crust through which the magmas is sent. So as the magmas assimilate crust, because it's so thick and hot, and mix with that crustal melt, they attain the isotopic composition of that crust. So they are a probe for crustal domains. So that is the spatial variation. So magma composition changed during the Andean crustal thickening. Crustal assimilation strongly affects magma compositions, and that changes through time. Now to the depth where this happens. We look at mineral compositions, and there are hornblends, and they have names, and they have different compositions. Just take it as we do it. The composition is a measure of the conditions where these minerals formed. You can calibrate the mineral composition to the pressure of formation and the temperature, and when you do that for the rocks from the Tarapacá, you find suddenly in the same rock the record of two populations of minerals that formed at different temperatures. Now, this is not so surprising. If you have two magmas mixing that have different composition, they also should have different temperatures. And this is what you see here. So these are the details, what we used to calibrate. So there's a level of mixing at around, say, 6 to 12 kilometers. And now to Paina Cotta, this is the background, the Tarapacá data, same thing. Yeah, there's some low temperature, some low and high temperature. Some are dominated by the high temperature. Same story over again. Okay, and then remember there was a collapse. After the collapse, everything changes. The magmas come from deep, they become more mafic. The mixing and eruption rate is much higher. So there's fast and deep recharge after the sector collapse. Basically, you can see the ascent of magma from their roots here into the shallow reservoir where the resident silicic magma is sitting, and it mixes with the new recharge. So there are vastly different regimes. Now, how fast does this go? We look at minerals, and the minerals are chemically zoned, and they are nicely zoned, and this is the barium concentration, like tree rings, and we can use that and map it out across one of these interfaces where magma mixing has taken place to cause the difference in the composition. These breaks in composition were smoothed out later by diffusion, and when you know the temperature and you know the diffusion coefficient, you can calculate the time the crystals spend at high temperatures. And we find that this ranges from about 30,000 to almost 500,000 years. So these are the resident magmas. They sit around for a long, long time, and then the recharge comes in and activates them over time. This is data that was done in Axel Schmidt's lab. It's still not published. This is the eruption times. This is the age of zircons in those dacites and roya dacites. This is titanium, is a measure for temperature. So there's a temperature and time history in the resident magma before they erupt. But that changes through time. For those who know this kind of diagram, just take it as it is. As long as you find rocks along this line, chemical change evolution is a long time ago. Chemical evolution and change in trace element ratios that is not a long time ago will displace you from that equiline in the middle. And when you do the calculations, it's about 20,000 years. The green is from the old cone Paina Cotta, and this is after the collapse. So things change dramatically between the story before collapse and after collapse. So we have a young cone, is a fast regime, old cone is a slow regime. So this is basically the story. There's a resident magma that cycles in temperature because there's mixing and new recharge, but it is sitting there for maybe 100 or 200 or 300,000 of years. And then things change. You have an enhanced recharge that activates those resident magmas, and the ascent and differentiation of these magmas is less than 20,000 years. So there's two very different regimes, the fast and slow magma regime, and they reflect different recharge rates from depth. And actually, it's shown at the surface, eruption rates are dramatically different from 0.3 kilometers per 1,000 years to 10 cubic kilometers per 1,000 years. Okay, summing up, we have different regimes. I did not talk about Aucankilcha. It is a volcano that is active for more than 5 million years. Come on, it's not coming. Okay, there we go. Then we have Tapaka regime. It's a slow regime. It's a lazy regime doing the same thing over many, many hundreds of thousands of years. And then you have the old cone regime of the Paina Cotta volcano. It doesn't come. Come on. Can you move it forward? No, there we go. I don't know why it takes so long time. You have the old cone regime, hundreds of thousands of years, and then only tens of thousands of years, the young cone regime. And the difference between the different regimes is just the increasing recharge rate from the base of the crust. So rhyodicite end members are processed in the lower crust. They ascend to shallow level reservoirs and just stick there. The lower crustal reservoir can be bypassed, and then you have mafic recharge, reaching the shallow level, heating it, mixing with it, and eventually erupting it. And it is either the slow system when you have a low recharge rate, or it's a fast system when you increase the recharge rate, and then you can go actually to the breakthrough regime where you hardly see anything left from those the resident magmas. Okay, it was mentioned that you can read more about this in the Elements issue of August last year. So if you're interested in it, go to the website. And that will be it. Thank you. I hope I made some case of different sources, different routes, different regimes of magmatism in the Central Andes. Thank you.
Thank you very much, Gerhard. Are there questions for our speaker? Yes, please. Can you use the mic? Yep.
So you showed this figure in the end where you have the different levels where magma accumulates, and you also showed that there's geophysical evidence for the upper reservoir. Is there also evidence for this lower region in 70 kilometers?
There's no direct evidence. Sorry. There's no direct evidence in terms of geophysical evidence. However, when you look at the composition of the magmas that come from that depth, they have the signature of high pressure magmatic processing. That is, the role of garnet is important, and that will change this ratio samarium-ytterbium, and you can only do that if garnet is part of the magmatic processing, and for that you need a minimum pressure, and that places you around 50, 60 kilometers minimum. So that is the evidence.
Okay, thanks.
I think that we can stop the question here, but there will be time for questions afterwards. Thanks a lot, Gerhard, thanks a lot. And I'm going to present the next speakers for this morning. Carmela Garzione is professor at the Department of Earth and Environmental Science and director of the Center for Energy and Environment, University of Rochester. She holds a PhD from the University of Arizona and has been a visiting research associate at the University of Colorado Boulder. Carmela Garzione was awarded the Donath Medal, Geological Society of America Young Scientist Award in 2007, and became a GSA Fellow a year later. She was AAPG Distinguished Lecturer in 2008 and 2009. Carmela Garcione's research interests are in the tectonics and climatic evolution of sedimentary basins and related mountains belt. She has worked extensively in the Central Andes, Peru and Bolivia, to document the elevation history and the tectonic evolution of the Altiplano Basin in order to understand the geodynamic processes responsible for surface uplift of the Andean Plateau. And this is what Carmela is going to present to today, so building the Central Andean Plateau. I would like to welcome Carmela on the stage. Thank you.
So first, I just want to thank the conveners for inviting me. It's a real honor to be part of this session celebrating the 250th birthday of Alexander von Humboldt. And as we've heard in several previous talks in the introduction, Alexander von Humboldt was the first Earth system scientist. His colleagues would describe him as an interdisciplinary scientist who sought to unify diverse branches of scientific knowledge. He preferred a holistic approach to viewing the Earth as interacting systems. And he even speculated on the role of humans and their influence on Earth's environment. And so he was really pushing the forefront of science in his age, but really the principles that guided his science are the things that we strive to push science toward in the present and future. And so today, I'd like to view the Central Andean Plateau in the context of interacting systems. And so we're going to think about systems from the surface uplift history and what they record about climate and paleoecology. We're going to go through the crust and even think as deeply as the mantle in terms of its structure. I also want to acknowledge numerous scientists who have collaborated, in particular on this continental dynamics project, as well as tectonics program grants at the NSF. And so the main focus of the discussion today is going to be on the Central Andean Plateau. I'm going to spend most of the time just talking about processes that have built this plateau. But toward the end, I just want to introduce some ideas about what pre-existing conditions might be necessary to eventually get to the wide, high elevation plateau we see today. And so I'm going to largely focus on this region, the Altiplano Basin, which is an internally drained basin that currently stands at about 4 kilometers On the west, it's bracketed by the high-standing Western Cordillera, the magmatic arc of the central Andes, and the Eastern Cordillera is a bivergent fold and thrust belt that has accommodated most of the shortening in the Andes. This region is largely inactive today in terms of shortening, and a lot of the shortening is being taken up in the foothills of the Andes in this region called the Subandean zone. And so, as has been highlighted previously, this region overlies a region of normal dipping subduction on the order of 30 degrees. And so some key long-standing questions in the Andean Plateau are what geodynamic processes have built the plateau? And it is well understood that long-term crustal shortening and thickening is a very important ingredient for building plateaus, and that this crustal thickening eventually accommodates the isostatic support for the high standing range that we see today. And so, the question is whether this is a gradual surface uplift process or whether there are other geodynamic processes that cause this thickened crustal lithosphere to rise dramatically or over short time spans. And it's also important to point out the role of magmatic addition in isostatic surface uplift of the Andes, and this has been well documented in several locations. But we also need to consider the potential of delamination or removal of lower lithosphere, being shown here, as accommodating rapid pulses of uplift as you remove this dense material that serves as an anchor at depth. And we also need to consider the redistribution of thickened crustal material by middle or lower crustal flow from regions of higher elevation and thicker crust into regions that have seen relatively less shortening. And so I want to give you some context for the geologic evolution of the Altiplano Basin, where a lot of this work has been done. In the early history of this region, you could consider the Altiplano Basin as a foreland basin. It was within a foreland basin setting with the Western Cordillera and a Proto-Andean fold and thrust belt to the west. By about Eocene, early Middle Eocene time, deformation had propagated and made a large step eastward into what is now the Eastern Cordillera. And by late Eocene time, the Altiplano Basin was an intermontane basin that was receiving sediment from all sides, basically internally drained since that time. And so, one end-member model for the surface uplift of the Altiplano, and perhaps a long-standing paradigm in geological sciences and mountain building, is that crustal thickening is the main contributor to surface uplift, and that this continuous process gradually builds crustal thickness, which supports the elevations that we see through isostasy. However, it's important to realize that thickening leads to gradual surface uplift, assuming that there's no thickened mantle lithosphere holding the surface down. And so if you're thickening the mantle lithosphere beneath this region at an equal rate to the crustal lithosphere, then you'd see minimal to no surface uplift. Surface uplift rates close to zero or very low surface uplift rates. And so to really accommodate isostatic support of this thickened crustal region, you have to somehow remove the mantle lithosphere. And it's been proposed that this is done gradually through subduction of the Brazilian mantle lithosphere, which is carried down into the subduction zone. And so, under these conditions, you could generate slow rates of surface uplift that occur over long time spans. These would be crustal shortening that is where deformation is coupled with surface uplift, and so you could see this surface uplift taking place over the same timescales as crustal shortening. On the opposite end member, there may be several mechanisms that lead to rapid pulses of surface uplift. And so by rapid, we mean on the order of more than a half a millimeter a year, so half a centimeter a year, to a centimeter a year over several million years. And so in this view, there's still underthrusting of Brazilian lithosphere, except for that material would tend to accumulate at depth, forming a thick mantle root, as well as, during crustal thickening, a zone of eclogite formation at the base of the crust. And so once crust exceeds 45, 50 kilometers, the lower mafic crust is converted to this ultra-high density material, eclogite, which is even more dense than mantle lithosphere. As this region thickens, eventually it begins to flow, and once it starts to flow downward, it does so super exponentially, potentially being removed over time spans of a few million years. That would result in rapid pulses of surface uplift over a few million years. Yet another mechanism to accommodate rapid surface uplift is a lower crustal flow, where regions of relatively thick crust, say the magmatic arc, or the region of crustal thickening in the eastern Cordillera, heat up as this crust is pushed to deeper geothermal, to deeper depths. And eventually this material is capable of flow. It flows from relatively thick regions into relatively thin regions that have experienced less crustal shortening. And so that jacks up the crustal thickness and thereby raises the surface. Again, this process is proposed to occur over a few million year time periods. And so a lot of the work that I'm going to describe today is based on methods of paleoelevation. And I have to say that if there were mass spectrometers in the late 1700s or early 1800s, I'm certain that Humboldt, based on the types of measurements that he was taking over elevation gradients, would have come up with the idea of paleoaltimetry and probably put this, these approaches to practice. And so these methods are largely based on observations of changes in the isotopic composition of rainfall. This rainfall experience is Rayleigh distillation, which removes the heavy isotope of O18 and deuterium. And so we see decreasing delta O18 values with altitude. But there are also methods, particularly clumped isotopes, clumped carbon and oxygen isotopes, which give us surface temperature information. And as surface temperature scales with elevation, we can use records within mountain belts of temperature change and isotopic composition change of rainfall to track the rates and timing of surface uplift over time. And so I'm not going to go in detail into these methods, but I am going to compile some of the results of the application of these methods to look at the growth history of the Central Andes. And so I've been working with numerous collaborators in this region over the past 15 or so million years, and so these dots, 15 or so years, I'm not that old, and so these dots show a wide range of sites that we've worked on, as well as other sites for paleobotany, work by Kate Gregory-Wadzicki. And so this is one of the first results that we published from the Central Andes, where we did the earliest work, and compiles multiple proxies that tell us about elevation, shown on the vertical axis over time, with time younging to the right. And the first kind of significant observation was that between about 10 and 6 million years ago, in the central Altiplano, we see a large magnitude surface uplift event on the order of several kilometers. And this is a result combining paleobotany, oxygen isotopes, which tell us about rainfall composition, and clumped isotopes that tell us about surface temperatures. So from there, we expanded outward, first to the southern Altiplano and eastern Cordillera, and then later to the northern Altiplano, to try to understand if this event was represented across the Altiplano in various locations. In the southern Altiplano, the region is too dry to apply conventional stable isotopes, and so we applied clumped isotopes to get at temperature reconstructions. And that region shows an earlier surface uplift history beginning between about 16 and 13 million years ago. Looking at the northernmost Altiplano, we applied a number of proxies, including deuterium from leaf waxes, oxygen isotopes from carbonates, pollen, all of those methods combine to give us a slightly younger surface uplift history than the central Altiplano, mainly between about 9 and 5 million years ago. We didn't just restrict ourselves to the late Miocene, Pliocene time intervals we see in the Altiplano. We looked at other evidence of surface uplift from potentially older time periods as well. And so jumping eastward to the Eastern Cordillera, so this again is the region of the largest magnitude of crustal thickening in the Andes. And there's an intermontane basin, the Saya Basin, which sits in the back thrust belt of the Eastern Cordillera. And so these deposits range in age from about 25 million to about 17 million years ago. And multiple proxies, both temperature, surface temperature proxy and a rainfall proxy, indicate similarly large magnitude of surface uplift of the Eastern Cordillera between about 24 and 17 million years ago. And so the goal of this work really was to get an integrated picture of the topographic evolution of this plateau, not just at these individual points, but also using these points as well as information from the flanks. And so this map provides a summary of a lot of different sites, our own as well as others' work, and connects those with incision histories from canyons in the Western Cordillera and the Eastern Cordillera, which tell us about relief generation on the flanks of the Andes. And so pulling that information into one picture in this very busy diagram, we've attempted to look at the topographic evolution of the Central Andes from the northern Central Andes and plateau in Peru through the central Altiplano, through the southern Altiplano. And so each of these diagrams shows the topographic evolution from the oldest time period in the top panels to the youngest time period in the lower panels. The blue shows the modern topography of these regions, and the red curves show hypothesized or measured elevation information from proxies and incision histories. And so these dashed lines on the flanks of the Andes represent places where incision history was used to estimate the magnitude of relief generated over certain time periods. And these dots show the sites where there are paleoelevation proxies. And so the main panel I want to focus on is the Central Andean Plateau, where we have the most information. And really our earliest records of paleoelevation come back to this time period about 24 to 25 million years ago, where we see that the Eastern Cordillera was relatively low standing at about 1.5 kilometers at that time. And what's interesting about this time period is that most of the shortening that is accumulated in the Eastern Cordillera had already taken place. And so despite that high magnitude of shortening and presumably thick crust, the region stood relatively low. Between 24 and 17 million, the Eastern Cordillera experienced a large pulse of surface uplift. And then between 10 and 6 MA, both the Eastern Cordillera and the central portion of the plateau, the Altiplano Basin, experienced another pulse of surface uplift. So the northern and southernmost Andes, we don't have enough data to look at the extent of this growth of the Eastern Cordillera. But we can see pulses of Altiplano surface uplift, again, in middle Miocene in the southern Altiplano and in late Miocene, Pliocene in the northern Altiplano. And so in the next couple of slides, I just want to go through the case for these end-member mechanisms for rapid surface uplift. And so really, here are lines of evidence we should be looking for if convective removal of the lower lithosphere is an important process in generating rapid surface uplift. I've already mentioned that crustal thickening precedes surface uplift of the eastern Cordillera. Most of the surface uplift or crustal thickening accumulated in that area occurred prior to 25 million years ago. And since about 15 to 10 million years ago, that region has experienced very little deformation. In the next slide, I want to consider the role of pulses of surface uplift of this nature in generating an outward jump in deformation. And so if this region increases in potential energy, it internally experiences a decrease in the rate of shortening. That drives deformation outward to low-lying surrounding regions. So is there evidence for that? So again, earlier we discussed that the southern Altiplano experienced its main phase of surface uplift between about 16 and 13 MA, whereas the central and northern Altiplano experienced its main phase in the late Miocene. So let's look for evidence of whether we see outward growth of the east of the subandean zone at that time. Oops, I think I went the wrong way. Here we go. Okay, so indeed, this earlier pulse of surface uplift is associated with earlier deformation of the subandean zone in the southern Altiplano, beginning in middle Miocene time. Likewise, in the northern Altiplano, central northern Altiplano, we see deformation stepping outward into the subandes at about 6 million years. And this is determined from low temperature thermochronometers, which show rapid rates of cooling, vertical cooling over depth, over younger time period, older time period, middle Miocene in the south, and younger time period, late Miocene in the north. At the same time, looking at paleoecological records from the high Altiplano, mainly plant carbon isotope compositions from fossil teeth and paleosols, we see considerable aridification of this portion of the Altiplano in the middle Miocene and this portion of the Altiplano in the late Miocene. And that's supporting evidence that surface uplift has occurred, which resulted in more arid climate conditions on the plateau. And so basically, we do see an outward jump in deformation during time periods where we have evidence of surface uplift. I think a couple of my slides are out of order, and so I want to go back to this high-density eclogitic lower crust as potentially driving lower lithospheric removal. If this is the case, then we should see accumulation of crustal thickening in excess of the modern crustal thickness. Basically, crustal shortening histories would generate greater crustal thicknesses that are actually observed in the plateau today, indicating that some portion of the lower crust was removed. And so in this complicated diagram here, we are looking at crustal thickening histories. And so first, let me explain the diagram. Here we've got elevation on the vertical axis here, over time, younging to the right. And this gray, this set of bars shows our proxies for paleoelevation. And so time periods where we've got steep slope between these bars are the pulses of rapid surface uplift. On the right, we have predicted crustal thickness from balanced cross-section reconstructions. And so looking at balanced cross-section reconstructions over time, we can convert that to crustal thickening. And so the gray curve here, the gray band here, shows the estimated crustal thickening over time based on balanced cross-sections. And so the question is, do we see excess crustal thickness? When looking at the crustal thickening history compared to the surface uplift history, we do see crustal thickness beginning to exceed the modern crustal thickness in the Altiplano over the same time span when rapid surface uplift occurs. And so we exceed crustal thickness in the Altiplano after about 10 million years ago, and that corresponds with a pulse of surface uplift, suggesting that some Altiplano lithosphere, lower lithosphere, may have been removed. The same is true for the eastern Cordillera. And in fact, the modern crustal thickness estimates or the crustal thickening estimates for the Eastern Cordillera are vastly larger than the modern crustal thickness of the Eastern Cordillera, telling us that somehow this material has been removed. If you look at the timing of that crustal thickening excess, it occurs at about 20 million years ago, again, over the same time span of rapid surface uplift of the Eastern Cordillera. And so lastly, we should see crust and mantle structure that's consistent with evidence of recent or ongoing removal. And so in the last panel here, I just want to take a look at crustal thicknesses in the eastern, or in the Altiplano zone. And so here we see some of the largest crustal thicknesses in the central Andes in excess of 70 kilometers. Interestingly, those crustal thicknesses occur largely under the Altiplano. In addition, when we look at the MOHO depth, so this is a crustal thickness map from receiver functions, when we look at the depth of the MOHO, there are portions of the Eastern Cordillera which have seen the largest magnitude of crustal thickness that actually have very low crustal thicknesses compared to their crustal thickening histories. And so this step in the MOHO is inferred to be a potential region of lower crust removal. And so I also want to point out that looking beneath the mantle at depth, we generally see relatively slow mantle in terms of mantle S-wave velocity, but there is a region of relatively high-speed mantle that's inferred to reflect portion of the lower lithosphere that's still attached beneath the Altiplano. This specific region is associated with some of the lowest elevations in the Altiplano. So again, suggesting that some portion of the lower lithosphere in this region is holding the surface down relative to the regions to the east and west. And then I want to quickly look at the case for lower crustal flow. And so the modern crustal thickness in regions of lower crustal flow should exceed the crustal thickening that can be accounted for by shortening, okay? And so rapid surface uplift of these regions would occur in the absence of crustal thickening, in the absence of crustal shortening. And so crustal thickening would be generated by some other process other than shortening ongoing at the same time. And lastly, exhumation and incision events should track both crustal thickening and surface uplift, but again, this should occur in the absence of shortening. And so if we look at the northernmost part of the Altiplano, again in this region of highest crustal thickness, we see very high elevations in this region, but a relatively low magnitude of crustal shortening, certainly not enough shortening to be able to account for the modern crustal thickness. In addition, this region is associated with a mid-crustal low velocity zone. This is S-wave structure from ambient noise tomography. And this is inferred to be a region of partial melt, potentially crustal material that's capable of flowing. So if we look at the cross-section reconstructions of this region, again, looking at this for crustal thickening history, we can see that this region has not experienced enough thickening to achieve the modern crustal thickness in the northernmost part of the Altiplano, shown in the black dashed line. And so somehow you have to fill this gap of the crustal thickness that's there in some other way. Yet another important observation comes from lanthanum-ytterbium ratios. So garnet present in the lower crust. It takes up heavy rare earth elements. So lanthanum-ytterbium ratios that are high would be associated with partial melting of lower crust that has eclogite. Okay? And so that tracks crustal thickening history. We see a major increase in lanthanum-ytterbium ratios over the past 5 million years, suggesting dramatic thickening of the lower crust at this time. And so basically, we see crustal thickening that occurs over recent time periods when there is no crustal shortening going on, and that these crustal thicknesses are in excess of what can be accommodated by the crustal shortening history. So these observations imply crust has been flowed out into this region from other regions of thicker crust. And so just to summarize, we do see a pulsed nature of surface uplift. So some of the major observations are that the central Andean plateau shows multiple pulses, at least two, one in the early Miocene, Eastern Cordillera specifically, and then one in the late Miocene in both the Eastern Cordillera and Altiplano. In the Altiplano, rapid surface uplift seems to propagate from south to north, from middle Miocene in the southern part of the Altiplano to late Miocene, Pliocene in the northern. And this just highlights some of the sort of more significant or maybe newer evidence that both removal of lower lithosphere as well as crustal flow are important processes. So when we look at crustal thickening predictions from balanced cross sections, there are regions where crustal thickening exceeds what can be accounted for by crustal shortening. And so this suggests that that thickened crust, in particular the lower crust, has been removed by a convective removal process, possibly involving high-density eclogitic lower crust. In the northernmost portion of the Andean Plateau, we lack the magnitude of crustal shortening required to account for the modern crustal thicknesses that we see. And so this suggests crustal flow into this region, possibly from the central Altiplano, Eastern Cordillera, or even Western Cordillera. And then this is consistent with observations of dramatic crustal thickening over the past 5 million years in the absence of crustal shortening in the northernmost part of the Altiplano, again, implicating crustal flow into this region. And so if I have time, I want to take the last couple of minutes to look at another region that looks a lot very similar to the Altiplano and is potentially a candidate for the development of a plateau. And so I want to compare the Altiplano to the Colombian Andes and think about what about this region could lead to plateau formation in the future or might limit its future as a plateau. And so we want to think about just the deformation over a broad region and the role of rift inversion, internal drainage of central basins, such as the Altiplano, crustal thickness, and in particular, the role of forming lower crustal eclogite, as well as the potential role of subduction geometry. And so comparing the width of the central Andean plateau to this region in the Colombian Andes, we essentially see the same width, about 400 to 500 kilometers in the widest portion of the central Andes, with similar widths in the Colombian Andes. We also see generally low-lying basin of the Magdalena Valley in the Colombian Andes, separating high-standing ranges, the Western and Central Cordillera from the Eastern Cordillera in the Colombian Andes. And so one of the similarities between these two regions is that this wide region of deformation is in part controlled by prior rifting. And so when we look at the Colombian Andes, the Central Andes, this zone of purple to blue represents late Paleozoic through Jurassic rift, and the red are rift plutons, rift-related plutons. These thick black lines with the teeth represent the back thrust belt and the forethrust belt of the Eastern Cordillera. And again, the Eastern Cordillera perfectly bounds this rift system, which indicates that inversion of this rift was in part responsible for the growth of the Eastern Cordillera and potentially the very large step from deformation in the western part of South America to so far east. We see the same process controlling the deformation of the Eastern Cordillera in Colombia. And so this relatively recent work reconstructs deformation history from a Cretaceous rift system in Colombia. And we can see that in the early part of the Cenozoic, these rifts were still observable. However, by about late Eocene, early Oligocene time, the beginning of rift inversion started to accommodate shortening of the Eastern Cordillera, and that largest magnitude of shortening largely feeds the inverted thrust faults that occupied these previous rift structures. When we look at the overall topographic characteristics of the Central Andean Plateau compared to the Colombian Andes, they're similar. And so the modern plateau has two high-standing ranges separating a relatively low altiplano basin, as does the Colombian Andes. The main difference is the altiplano stands at 4 kilometers, and the Colombian Andes stands at only basin only stands at a few hundred meters. However, if you look back between about 20 and 10 million years ago, the Central Andean Plateau looked very similar to what the modern Colombian Andes does, with an Eastern Cordillera that stood high and a Western Cordillera that stood high relative to a low altiplano basin. The modern Colombian Andes really looks similar to what the Central Andean Plateau would have looked like between 20 and 10 million years ago. And so if we look at deposition in the Central Andean Plateau, we see extremely high rates of deposition on the order, producing on the order of 10 kilometers or more of sedimentation. And certainly this contributes to the crustal thickening history of the Altiplano. However, a distinct difference in the Colombian Andes is that this central basin has external drainage. And so the Magdalena Valley is being drained by the Magdalena River, which is continually excavating the basin fill that occupies this relatively low-lying basin between the eastern and western ranges. Looking at crustal thickness in the Colombian Andes versus the Central Andes, again, we see 60 to 70 kilometers, in excess of 70-kilometer thicknesses in the Central Andes. This map shows crustal thicknesses in the Colombian Andes, and we achieve crustal thicknesses on the order of about 55 to 60 kilometers. Both of these regions are capable of generating eclogite in the lower mafic portions of the crust. Now, if we overlay the topography with the crustal thickness in Colombia, I think it's interesting to note that the largest crustal thicknesses are not necessarily associated with the greatest regions of crustal shortening. And so, in fact, they're mainly located near the Magdalena Valley and the western edge of the Eastern Cordillera. And so it's interesting to note that crustal thicknesses are offset from the regions that experience the greatest magnitudes of crustal shortening. And so what does that mean in terms of isostasy? First, I want to point out that earthquake locations have provided information about the geometry of the subduction zone. And so we see relatively flat slab subduction north of this red line, which is inferred to be a tear in the Nazca plate subduction, with dipping subduction further to the east near the Eastern Cordillera. South of this zone, we see steeper subduction. If we look at the crustal thickness, that's used to calculate residual topography, and so deviation from what you'd expect if isostasy were driving the elevation produces high residual topography in regions where crustal thickness cannot produce the actual elevations that we see. North of this tear in the subduction zone, we see high residual topography beneath the Eastern Cordillera. Basically, the crust here is too thin to support the topography that we see. Likewise, along the Magdalena Valley, we see high magnitudes of crustal thickness that are associated with low elevations. And so again, this just underscores that this region is not an area isostatic balance. And so, we can think about the role of slab geometry in this question. So if we look at inferred evolution of the Central Andean Plateau slab geometry, this is largely based on arc magmatism. Between about 35 and 25 MA, there's inferred flat slab subduction. Between about 25 and 20 MA, the return to deeper or steeper slab subduction, as well as inferred removal of some of the lithosphere beneath the Andes, has been hypothesized to have caused early surface uplift of the Andes. When we look at the modern slab geometry of the Colombian Andes, north of about 6 degrees, we see flat slab subduction extending right to the western edge of the high-standing Eastern Cordillera, and the Eastern Cordillera sitting much higher than crustal thicknesses would suggest. And so this is a inferred evolution of that flat slab subduction, largely based on the timing of volcanism and its eastward march north of 6 degrees. And so these authors infer that slab dehydration changes the density of the mantle wedge, which provides some of the support of the Eastern Cordillera. And so I don't really want to draw any conclusions about this. I'm hoping it just generates some discussion and really gets people thinking about what's really necessary to ultimately build a plateau. You know, this is a list of some things that seem to be necessary to build a plateau, but there may be other things, and hopefully we can just think about that and discuss that. Thank you.
Thank you very much, Carmela. Are there questions from the audience? Yes, few.
I enjoyed your talk very much.
Thanks.
As a geonemesis, the first expectation you would have is there's a rapid uplift. Then there could also be associated with that a rapid change mode in the plate motions. Do you think that that kind of combination would help to provide further constraints on uplift questions?
I don't know. So I think I'm more comfortable thinking about uplift in terms of isostatic response. And so I can imagine plate motions playing into the change in balance of isostasy and mantle dynamics. But I think I've always tended to think more about the role of isostasy and density changes in the mantle as well as the crust as being the main components of, or the main drivers of changes in elevation.
Very nice. Then I would simply say that I would expect that correlation, and that would be nice to investigate.
Thank you.
Yes, please.
Hi, Carmi. Thanks for the talk. I'm just curious, there have been a large number of studies now that have documented that there's thresholds in climate change that occur as the plateau goes up, and that these influence almost all of the paleoaltimetry data you've shown.
Right.
And can also show non-uniqueness in how river incision is interpreted, for example, that it could be climate change or surface uplift. And when you come to the conclusion that there have been pulses of uplift, I'm a little bit concerned because your elevation reconstructions you showed did not have uncertainties on them. And I was just wondering if you could please comment on how confident you can be about these pulses of uplift when climate change has been documented.
That's a great question. And so Todd is a co-author on the annual reviews paper. And of course, we, coming from different perspectives, went around and around about how to present these results. I do want to mention that the surface uplift estimates that I showed are the most conservative in terms of magnitude of surface uplift. And so we did consider the potential bias, and basically what we, the bias leads to a lower paleo elevation for time periods when elevation would have been lower. And so we used the highest elevation estimates. And I do want to clarify, Todd, that the surface uplift estimates that we showed use a climate correction from the modeling that we did with you and Chris Polson. And so although I did not show uncertainties in this, I think I'll call it a cartoon representation of paleotopography over time. The uncertainties are represented in the studies that this is based on, and they do incorporate a climate correction that takes into consideration the role of increase in convective precipitation with higher elevations. And so again, that pushes us more to the conservative end member of magnitude of surface uplift.
Karina is a geologist, paleoecologist, and associate professor at the at the Institute for Biodiversity and Ecosystem Dynamics of the University of Amsterdam. In 1994, she obtained her PhD at the university, this university, and in 2003 obtained a master's degree in science communication at Imperial College London. In 2018, she was a visiting scientist at the Xinyang Institute for Ecology and Geography in China through a fellowship of the Chinese Academy of Sciences. Karina's long-term research interest is in the natural history of Amazon region and its seaward extensions, the Amazon fan. She made a substantial scientific contribution by identifying the crucial role of Andean uplift on the evolution on Amazonia during the Cenozoic and recognizing the Neogene marine incursions into this region. She currently participates in the Trans-Amazon drilling project scheduled to take place this year. She has recently co-edited the book Mountains, Climate and Biodiversity, and is a member of the organizing committee for the Humboldt conference to take place in Ecuador later this year, but I know that Karina is going to introduce that. So please, Karina, the stage is yours.
Thank you very much for that nice introduction. Thank you for being here. And thank you to the organization for bringing together us here in this symposium to celebrate Alexander von Humboldt's birth year, his 250th. So we have heard already that Humboldt had many scientific facets to him. And in my presentation, I would like to speak about his role as botanist and as founding father of plant geography, and by extent, by the field biogeography. And he came to his most defining working in the northern Andes. And there he got his idea of the interrelatedness between plants in their distribution and relation with, for instance, temperature and environmental variables. So I would like to argue as well that in his later years, after his death, his way of science got really a bit out of fashion. The scientific discipline started separating. However, I would like also to show you that in recent years, there has been a sort of revival of the Humboldtian type of science. And I hope to show you some examples from the northern Andes where biodiversity studies are taking this interdisciplinary approach of geology, climate, and biological sciences to come to a better understanding of the origins of biodiversity. So Humboldt was born in the 18th century, and he lived well through to the 19th century. And this was the era of exploration, big expeditions around the world, Captain Cook traveling, many scientists collecting a lot of data, mainly species, and describing species. At that time, though, the interrelatedness, the distribution of taxa and the relation between them was not recognized. However, at the end of the 18th century, there was a movement, and this had some very important representatives. And in fact, the philosopher Immanuel Kant was one of the first to suggest that taxa, species, could be described in different ways. It could be either in sort of collections, comparing, but you could also look at it in a historical perspective or in a geographic perspective. And there were other scientists at that time that were all contemporaries to Humboldt, such as Willdenow and Forster, who traveled with Captain Cook, who realized that there was a relation between species. And so there was this movement in the end of the 18th century to move from purely describing to recognizing these processes. And so Humboldt actually was, as I said, contemporary, but he was the one who was able to really synthesize this and represent this notion in a way that transcended to, well, over the centuries. And this view of him, this recognition of the relation between species and environment is a cornerstone of the field of biogeography, which studies the connection between the geographic space and geologic time. And also, in fact, the field of ecology does this. Humboldt was not the only one that you could call the founding father of biogeography. He was mostly focused on the distribution of plants, but the other famous founding father is, of course, Alfred Russel Wallace, who is also known for co-developing the theory of evolution. And Wallace was, well, inspired by Humboldt, so he came to this at a later time than Humboldt, but his most important work is on the distribution of animals, so animal geography. So together they can be called the founding fathers of biogeography. So what then was this brand of science that Humboldt made so famous? And the name Humboldtian science came from Susan Cannon, who coined this in 1978. So his aim in science, and because I said already there was this precursor movement, his aim was move on from describing. He was a botanist and he collected many data, described many species with his colleague Aimé Bonpland, but his aim was to come to these geographical relations. And he said himself that the discovery of an unknown genus was to him far less interesting than elucidating these geographic relations. And so he had this view of relating, but at the same time, he also was very strong on collecting data. So if you would characterize this brand of science, it would be accuracy through extensive data collection, a skepticism to existing ideas and theories, and also new conceptual tools. You already saw the isothermal lines, how he showed this in a very compelling graphical way. He did the same with the his discoveries on the geography of plants. So Humboldt was born into a wealthy family, and in his initial years he trained as a geologist and he became a mining inspector. But as soon as his mother died, he inherited a huge fortune, and that's when he could pursue his dreams to set up expedition to go and reach out for his aims, which is looking into the unity of nature. And this trip, this expedition, these travels across the Americas lasted about 5 years. And it took about 2 years to prepare because he was very, as I said, driven to collect data. He liked to use the most modern tools at the time. They brought everything that he could get with his money to do all the measurements that at that time were considered the sort of forefront of science. And in this preparation, because it was also a time of war between Spain and France and England, so there was a lot going on. It was not that easy to do these trips. And whilst this preparation was going on, he met Aimé Bonpland, the botanist, and together they walked, as they did in that time, walked to Spain from Marseille. They crossed the Pyrenees, and already there, of course, they were looking at basically these gradients, altitudinal gradients. So finally, they managed to obtain permits from the King of Spain, Carlos IV, and they managed to sail from La Coruña to via Canary Islands to South America, and they first landed, in Venezuela, and that's where they started their expedition. First of all, to the Amazon, and then later on to the Chimborazo. And actually, they didn't set out to go to the Chimborazo. This was really a sort of chance because initially they were going to the Pacific. They were not going to venture that far. But then they found out that there was a ship sailing from Lima, and they wanted to catch that. So they said, OK, we'll do the Andes as well. And so that's how they got to that area. So the first leg of the journey was to the Amazon. And at the time, here you see Humboldt and Émile Bonpland. And this is supposed to be in 1800, but the painting is made much later, when he was already well famous because of these travels. And here you see him, like what equipment they had, an array of plants. And they collected actually an impressive amount of plants. More than 6,000 specimens were collected and brought to Europe. And they described about 3,000 species. And some of the most common species, if you go to the herbaria now, you'll see Humboldt and Bonpland as the ones who describe these taxa. So collecting was still a very important thing. And what they went to do in the Amazon was actually to look for the connection between the Amazon and the Orinoco. At the time that they traveled, this was sort of whispered. It was known that, or it was said that that connection existed, but the European scientists didn't believe anything of that because the science at that time didn't hold that for possible, that such big rivers could be possibly connected. And so the first reports were from Spanish religious man who already was there, and when they arrived in the region, basically said, well, of course we know this connection exists. Well, they go there, and in about 1800, then they map this area, they confirm this existence of this connection, which is called the Caciquiare, and of course they do all this collecting, which has been crucial. So from there, they went back to the coast, and as I said, were planning to sail somewhere else when they heard that there was a boat from Lima going to the Pacific. So they set off to catch that ship. And in those months that they had, they went across the volcanoes, met with South American scientists such as Mutis and Caldas, who also were envisioning this relatedness between geography and plants. So again, it was a whole movement that was going on both in Europe and also in South America. So it was during this journey across the Andes that really he started developing this thought of the relatedness while they were collecting data. So they went up to the Chimborazo from a foot to as high as they could get, which was not the summit because they stopped, I think, about 400 meters away from the summit. And it was whilst measuring temperature, humidity, the blueness of the sky, air pressure. All they could measure, they were measuring in a very high detail, and of course collecting all the plants. And here you still see this horizontal zonation, as we heard already. This later on is becoming sort of more diagonal as they realize that different slopes of the mountains have different altitudinal range. And it was here that they recognized this sort of zones of plants, ecological zones. And as he was a mining inspector long in his early years, so he already had been looking at subterranean flora. So in this altitudinal gradient, the subterranean flora is mentioned first, and then we go from tropical lowlands to mountain forest, paramo, and snowline. And basically, this is a sort of condensed zonation as is known from the tropics to the polar regions. And of course, Humboldt realized he had already traveled a lot, and of course, there was already quite some noise. So he realized that this altitudinal gradient was a sort of condensed version of the latitudinal gradient. In a later figure, this is from 1817, he shows one of his iconic images. He shows this relation between the tropical mountains, temperate mountains, where he uses the Mont Blanc, and a mountain in Lapland to show how these zones change depending on where you are in the latitude and how the snow line and the tree line and the diversity of plants changes. And of course, the most iconic of all is this figure, the Natuurgemälde, where he shows at scale the Chimborazo with on one side the vegetation and on the other side all the species names. And of course there's also an organization to this because this inclination of which the names are is actually meant to indicate the zones, taxa that range from one zone to another. And this was the key figure of the book that would lay out this science plant geography, because this was the central figure, the summary of all the knowledge that was obtained, and on the sides there were the abiotic variables were reported, and in the center, of course, the biota. So here an image of the book. This is actually a translated and commented edition from 2009. And in this book, he explains, it's almost like a letter to the audience in the style that they would use in the early 19th century, very different from the scientific communication as is used nowadays. So he explains the latitudinal gradient and his observations on the latitudinal gradients, and then in the second part of the book, the altitudinal gradient, and of course, reflecting on the Chimborazo experience. And here you see one of the first maps showing the knowledge obtained during this journey to South America, expressed in a plant geographic map. So what happens afterwards? So in the 20th century, his brand of science basically become almost like not obsolete, but the sciences divided into disciplines. So there was a separation. On the other hand, of course, the 20th century also saw the continental drift theory by Wegener, which already was using distribution, was using plant geography in his, when he formulated this model. But it was only in the middle of the 20th century that finally the mechanism for this continental drift was shown. And this, of course, had implications for understanding the plant geography. And so Peter Raven and Daniel Axelrod in 1974 then revisited the geography of plants in the light of plate tectonics. And of course, this you could consider a very Humboldtian approach to science. So if we make another skip forwards, at the end of the 20th century is the advent of molecular phylogeny, molecular studies, and basically all these plants that were described, the old collections, and the classification that exists at that time was being revisited. And so many ideas of which plants were related were redefined based on this sort of molecularly generated trees. And also, we entered the era of what they call the big data. So, big databases, which means, again, something that Humboldt would have been very pleased about, because he was an advocate for measuring and also establishing measuring stations around the world so that data could be compared in a sort of in the same time span. And so nowadays, of course, all these databases from soil data, from diversity, from climate and so on, they can be connected. So that's really a big step forwards for integrative science. So now I would like to move on to some examples of the sort of Humboldtian science in the 21st century and use some examples at the interface of biology, geology, and climate sciences, and bring forward this example of work that we did that was published last year, which was using databases, was comparing the abiotic variables with the abiotic variables and explore what is the relation between geology in shaping biodiversity. And so in the top right, you see a figure of the variables that were measured. So for instance, precipitation, temperature, and their different ranges. And then in terms of abiotic variables, geological variables, relief, erosion rates, soil, and so on. And what we found is that climate, of course, is a driver of biodiversity. This was suspected for a long time. But that also, especially relief and soil, are important mechanism for diversification in mountain regions. And if you look at these two maps, you'll see in the top map the distribution of the mountains, and in the lower map you see the vertebrate richness, biodiversity, the richness of vertebrate species around the world. And you can see this pattern, which on one side, of course, is the tropics are more species rich than the temperate zones, but also this relation to the mountains. And so this is something that you visually can suspect, but also came out from this quantitative analysis. And how does this mountain biodiversity then form? How do you get these zonations? What exactly prompts this? So on one side, of course, the mountain building, the uplift, creating this topography is what gives the opportunity for taxa to colonize this newly formed terrain. And this is a model that was produced by the German scientific group from Senckenberg and from Leipzig. And it was presented in the book Mountains, Climate and Biodiversity, and also in a Frontiers article. So that it's actually a two-step process. On one side, building this gradient, but on the other side, the climate change, for instance, as you have in the Quaternary climatic variations, this glacial, interglacial variation, does a lot in reshaping the landscape. So this erosion and valley formation really creates a very heterogeneous relief environment. And that is being found to be crucial for plant biodiversity. Areas with high heterogeneity will be very diverse. They create an opportunity for speciation. So you get immigration of taxa into these regions and then a sort of species bump due to isolation and connectivity. So when did Humboldt's altitudinal gradient in the Andes then form? So I'm using here a map that was produced by Mauricio Bermudez, which was published in 2010. And I checked with him, and he says, yeah, it's still up to date, except, of course, there's more data now. But you can see here, and this, of course, coincides with what Carmela Garcione was already explaining in much more detail, how the uplift of the Andes has gone through pulses. And particularly in the pinkish colors, you see the recent uplift, and particularly in the northern Andes, this would be younger terrain formation, but you see it also, of course, in the central Andes. What does that mean for biogeography? Well, a work last year published by Hatzi et al. in PNAS addresses the biogeographic zonations, biogeographic regions in South America, showing this whole array of colors. I won't go into those details, but it's just to give you an idea that the big breaks, and they're a bit difficult to see, but I've highlighted one of them with the circle, the big topographic breaks are actually very important species barriers. And the geology often seems to play a role, and of course this uplift pattern creates these big topographic breaks. So these divisions are very important as driver, and it really remains to be analyzed what this map, how this can further relate to geology. I have some examples on how we can integrate for instance, the geological data with the molecular plant records to explain how are these areas of the Andes, for instance, these newly formed areas, how are they colonized by plants? So what happens, you create this relief. That means that taxa from temperate zones can immigrate into these newly formed mountains. So for instance, we get taxa such as this boreal one coming from the north, called Mallow family. And they arrive in the Miocene. You can see that in the map on the left. So they are known to arrive in South America around 70 million years, probably when you have the first mountain formation, fresh environmental heterogeneity taking place. And this and here you see the data such as the molecular, the phylogeographers produce them. So this branching is like the division of species. We won't go into the details, but you can see there's a lot going on here. But where you see these little circles, that's where the species arrives in South America, and then they adapt, and particularly in the Neogene, then they diversify in the Andean region. And you see also on the distribution, the modern distribution of the taxa, they have really colonized this Andes. So this is an example where we integrate geology and molecular data. And then I have another example where this is an example of the bellflowers. This is a taxon that actually originates in the south of South America. And they reach the central and northern Andes in the Pliocene, around 5 million years, and they diversify very fast. This is a species radiation taking place. And these authors, Lagomarsino et al., what they do is they test the geological data, and I think it's the curve from 2008 from Carmela, and they use this, and they use also the temperature and test how speciation and extinction relate to these altitude and temperature values. And this has become quite an influential paper, and I should say it's very important to have these geological data to test the speciation and extinction rate. And so this taxon radiated in the cloud forest, and it's shown that it does very well under this high elevation, and actually cooling doesn't affect it very much because there is low extinction during cooling. So it likes elevation and it likes cooling together, but this has been tested in independent ways. Oh. Doesn't seem to, oh, sorry. Okay, another example is, it's a bit delayed. Okay, another example is a study on the hummingbirds, where also uplift and temperatures were tested, and where it's found that in this case they do better with low elevation and they're favored by warm temperature. So another example of how these abiotic variables are important to understand the diversification of the taxa. Well, the alpine vegetation, the Paramo is the highest vegetation in the mountain belt, if you remember the altitudinal gradient. So this is the distribution of the Paramo, and this is a system that we know from the fossil record must have originated around 5 million years, and it's highly sensitive to climate change. And that's quite important to realize, because in this time of anthropogenic-induced climate change, what is happening to these groups? Just recently, a model was presented again in the Mountains book, and it's also being published in the Journal of Biogeography. A model is being shown here on what is happening during the Quaternary interglacial glacial changes. Because if this is such a sensitive system, of course, in the interglacials, it will be quite reduced. It's in the higher mountains. During the glacials, however, this Paramo system extends down the slopes and has a much bigger area. This also comes back to the hypothesis of the geobiodiversity. How do species originate in mountains? And it's this connection and disconnection that facilitates speciation. So again, both the uplift and climate change both trigger as a double whammy this high diversity in the Andes. Interestingly and incidentally, over 200 years after Humboldt went to the Chimborazo, a Danish team of Jens Svenning and Moretta Holm, they went back to the Chimborazo and checked what happened with the ecological zone. Has there been a shift of these vegetation zones? And they found, shockingly, that there was a 500-meter upslope move. So the Paramo and other taxa were retreating higher up. And they also found, other researchers found that there has been a 40% glacial retreat. So there has been quite a change in the time span of Humboldt going there and the Danish team going now. So that is quite shocking. I think my time is over, but I still would like to say a few things. Is that possible? Do I have time? Yeah, okay. So I've shown you some examples of that where biodiversity studies, the origin of biodiversity, is very much helped by accurate geological data, climatic data. However, there is a discommunication between the sciences. The geology, the biological communities, they have different meetings, they don't talk much together, they use different journals. And this leads to poor science sometimes. And Suzanne Renner observed in the Journal of Biogeography in 2016 that a growing number of studies by biologists are citing geological papers that are outdated or misciting information. And she uses an example of the Tibetan plateau, where there is a total bubble of misinformation and where hundreds of papers refer to the wrong information. So one of my messages, please help us, help the biogeographic community with accurate data. Consider publishing in these type of journals if you want to summarize and converse with other sciences. In 1959, there was a famous work, very famous among the social sciences, by C.P. Snow, who discussed the two cultures and the scientific revolution about the breakdown between communication between the sciences and the humanities. And are the geology and the biology like the apples and oranges in this picture? Can we do something about that? How did this happen? We know that Humboldt definitely envisioned something else. So my take-home message, I would like to say, let us think like Humboldt and consider what can geological data mean for biodiversity and biogeographic modeling. You see already with the climate change, it's very important to have accurate and up-to-date geological data incorporated in such models because it can lead to more effective conservation of global biodiversity. Well, something on Humboldt's lasting influence, as Juliana already mentioned, later this year in August we have a meeting in Quito where we will celebrate Humboldt again and we'll think about his geo and biodiversity links. There's also a special issue being made on this same topic, exploring the links between geo and biodiversity, which hopefully is coming out in 2019. And one of the papers will talk about challenges and opportunities for biogeography. What can we still learn from Humboldt? So I hope you will feel interested by this and that you will think about the biogeographic community and sharing some of your data. Thank you very much.
Thank you very much, Carina, for this perspective from a more biogeography viewpoint. Are there any questions?
I'm a Humboldt enthusiast and I enjoyed this very much, but I just wanted to point out that there is an English translation of a fragment of his diary that describes the loop on the Orinoco to Zacatecas, and that illustrates very well the personality of the man who was as interested in the languages of the Indian tribes as he was in the plants. So I don't remember the translator, but it's a Penguin classic or something.
Thank you. Yeah.
Do you know any works about the cold currents? Do you knowing already the cold currents lean down always, and the glaciers source of cold currents, they are laying down, and then the new species climbing up. It's at the same time glaciers little bit at back now. Yeah. And how is the effect of cold currents on flowers and the other plants?
The effect of cold currents, you mean cold air?
Yeah, I mean cold air.
Oh, you mean like upcoming air or so?
Yes. Actually, downcoming cold air from the glaciers. How effective about flowers and normal and other trees or plants?
I'm afraid I don't have an answer to that because I'm a palynologist, so I'm looking more at the fossil record. But the one thing I can say, which is sort of complementary, is that this retreat means that, of course, you have a risk of extinction of the cold mining species. But how they react to the cold airflow, I don't know. I'm sorry.
Oh, okay.
Carmela. Yeah.
I need to go to the microphone, or can I just yell?
I can hear you.
So I really appreciated the kind of characterization of the dual role of work between climate shift. Yeah, I really appreciated the characterization of the dual role of greater climate cyclicity in the recent, as well as the role of mountains in high biodiversity in the tropics. What would biodiversity in the tropics look like in the absence of glaciations? Would it be as high? Are the mountains and their role more important than climate variability over the past 3 million years?
I understand. I suspect, but this of course is speculation, that it would be less diverse. I have had to learn. Initially, I was very much focused in my work also on only the geological drivers, as in the changes in surface processes and topography. But I've learned through the work with the biologists who are studying the effect of the climate change that, yes, it makes a very big impact. So that's why I would like to say it's a double whammy. So it's so diverse because of this overprinting of these processes. However, I also wonder, what does it mean when the climate change happens? Because, for instance, in the Amazon basin, there have been very dramatic changes. So I think for the mountains, it has been a very positive. I wonder in the Amazon basin, I wonder if it's a resetting of the clock, if it has been wiping out a lot and then restarting. That's my speculation on that. And I think now I have to move.
Yeah, thank you very much, Carina. So our next speaker is Veerle van Akker. Veerle is a professor at the Earth and Life Institute at the University of Louvain in Belgium. She holds a PhD in geomorphology from the Universiteit Leuven and has been a Marie Curie postdoctoral fellow at the University of Hanover in Germany. Veerle obtained the Outstanding Young Scientist Award of the European Geosciences Union Geomorphology Division in 2012. She has been a visiting scientist at numerous universities in Europe, the USA, and Ecuador, and has coordinated the collaboration of her university with Ecuador in the framework of the Belgian Academy for Research and Higher Education. Veerle's research focuses on the anthropogenic and natural perturbations to geomorphic processes in mountain areas, and particularly in the northern Andes. So, Veerle.
So first of all, I would like to thank the organizers of the session. It's really a pleasure and an honor to be here and to present you the legacy of Alexander von Humboldt for the development of modern geographical science. So in this talk, I will take the opportunity to take you to the tropical Andes, where Alexander von Humboldt realized most of his work. And I will take also the opportunity to introduce some recent research debates in the field of physical geography. So mountain environments are fascinating environments. They provide us with extremely diverse fauna and flora, and are also home to culturally rich mountain communities. And so although these mountain environments, they cover only 25% of the land surface, they provide services and goods for more than half of the global population. And particularly in the last decades, there is a renewed attention for the freshwater supply that comes from these mountain regions, as there is a potential for scarcity for this water supply and water regulation under climate change. And so tropical mountains, such as the one that Alexander von Humboldt and his colleague Aimé Bonpland visited and described during their mission to the Northwest South America from 1801 to 1803, are extremely diverse. So we know that they host almost half of the global biodiversity hotspots, and also they host about 70% of the bird diversity. And so although these tropical mountains are highly diverse, we know relatively little about their impact by anthropogenic and by climate disturbances. And therefore, the observations that were made by Alexander von Humboldt and Aimé Bonpland 200 years ago are still very valuable in order to analyze the changes in the landscape over the last 200 years. And what is important that Aimé Bonpland and Alexander von Humboldt, during their ascents of these mountain tops and the ascent of Mount Chimborazo, they took a lot of observations. So they measured the elevation, the atmospheric pressure, and they collected a lot of specimens of plant and rock and soil material. And this laid the basis for the development of these well-known plant models, as we've seen in the previous talk. However, it's also sometimes forgotten that Alexander von Humboldt, he was also one of the first who noticed already the anthropogenic transformation of the landscape. And we can see this quite nicely in this drawing of Hildebrand, which is based on sketches of Alexander von Humboldt. And so what we can see here in this drawing, this is Mount Chimborazo, which is located in Ecuador. And this Mount Chimborazo is already surrounded by plains which are devoid of forest vegetation. And so Alexander von Humboldt, he describes in his book Ansichten von der Natur that these plains have been deforested extensively and that they are now that they are now populated by herds of llamas and flocks of sheep. And so he was one of the first to point already to the environmental degradation that was occurring at that time. And also he mentioned the degradation of the Andean forest, so the Chinchona forest, due to overharvesting. And so it's interesting to compare now the environment as we observe it in 1802 with the environment as we observe it today. And a very important work has been done by Naya Morwete Holme and colleagues and has been published in 2015, and we've seen this figure already in the previous talk. And so what they did is they've revisited the area of the southeast flank of Mount Chimborazo in 2012. And during their visit, they collected plant species, and based on their collections, they made new maps of the plant distributions. And so what we can clearly see on this figure are the following three things. We can see, first of all, that the upper limit of the vegetation has moved upslope. Second, we can also see that the vegetation zones, as they were defined by von Humboldt, so the region of Pajonal or the grassland vegetation, and the region of Geosciences and Chuquiragua, have also moved upslope by several hundreds of meters. And then we can also see the important retreat of the glacier by several hundreds of meters. So part of these changes in the vegetation distribution are clearly linked to global warming and the increasing mean temperatures. However, we can also see that a part of these changes are due to land use disturbances. And so on the right-hand side of this graph, we can see so the impact of climate and land use disturbances on the vegetation distribution. So land use change has an effect on all altitudes, while the land use change effect is mostly concentrated at the lower altitudes where we have agriculture and anthropogenic fires. And so in this graph of Morwete and all, we can see the changes in the plant distribution. So in the gray shaded area, we have the distribution of plants as von Humboldt recorded them, and the curves show us the distribution in 2012, and it gives us the relative abundance of a vegetation zone along the altitudinal transect. And so here again, we see the important upslope movement of the vegetation zones, which is also in correspondence with the glacial retreat and the global warming. But secondly, we also see, and this is quite important, is also an extension of this Pajonal or this grassland vegetation zone towards lower latitudes. And this is the result of anthropogenic disturbances, and I will come to that now. So these anthropogenic disturbances to the forest line have also been mentioned by Fadrique et al. In this paper in 2018. So at the scale of the tropical and the subtropical Andes, they have looked at changes in species distribution. And you can see here for the more than 200 vegetation plots that they monitored, in red we see plots where we have a thermophilization, so an increase of species from relatively warmer temperature. The blue dots are areas with a negative thermophilization. And so in general, most of these areas of the forest vegetation, they have a positive thermophilization. However, we also see that there are areas where the tree line is moving downslope, and this is linked to these anthropogenic disturbances. And so in this land use study, which is done on one of the slopes of Mount Chimborazo, we can see the changes in this vegetation over the last 5 decades. And what we can clearly see on these land cover maps is that, so in green we see the mountain forest, and we see that during the 70s, 80s, we have a very important decrease of the mountain forest. We see some transition going on from the 90s onwards, with a deceleration of the deforestation and an increase of forest plantations with exotic species at higher altitude. So in short, the vegetation distribution that we observe today in the Andes is strongly affected on the one hand by climate change and on the other hand by anthropogenic disturbances. And I will take you now in the remaining part of the talk to two environments. So the upper Paramo or the Pajonal vegetation zone, and then I will move to the mountain forest vegetation zone, where I will show you how these changes in the vegetation cover have affected Earth surface processes. So first of all, let's have a look at the Spajonal vegetation zone. So this is the vegetation zone between the perpetual snow line and the continuous tree line. It is located between 3,000 and 4,500 meters above sea level. And so if we look at this area, we can see that the vegetation is quite heterogeneous. And so we have typically these patches of tussock or bunch grasses, we have cushion-forming plants, and we have patches of thickets of polylepis forest. And so in this area, we were mainly interested what is the co-variation of the vegetation with the soil and with the landscape. And in order to analyze that, we were working with soil data, which were collected from 30 soil profiles along 10 toposequences. And by collecting these data and analyzing the soil biogeochemistry, we wanted to test two hypotheses. The first one is that the degree or the extent of the chemical weathering in the soil is independent of the vegetation type. And then the second one is that the degree of chemical weathering extent is independent of the topographic position. Now I will briefly or quickly read you through this diagram of Brantley, just to show you the indicators that we used in order to quantify the soil development. So our method was based on the method proposed by Brimhall and Dietrich, published in the 1980s, and uses a mass balance approach. So typically in this mass balance approach, you will use immobile or conservative elements in the soil and the rock in order to calculate fractional mass losses and gains in the soil matrix. And so typically, when we look at the volcanic parent material, we know this volcanic parent material is transformed into saprolite, and then by physical deformation and chemical weathering, that saprolite is transformed into soil. In order to quantify the soil development, we used the mass balance approach, and then we calculated three different types of indicators. The first one is the physical deformation of the strain. This gives you an idea of the volumetric changes in the soil matrix when the bedrock is transformed into soil material. This is the epsilon value as we observe it here. It's derived from the bulk density measure of soil and rock and from the concentration of an immobile element. Positive, so strain values above 1 means dilatation, below 1 is compaction. Then we looked at the chemical depletion by using mass transfer coefficients or tau values, and they give us the gain or the loss of an element compared to the bedrock. And then finally what we can do, so we can multiply these elemental tau values by the relative concentration of this element in the parent rock. We can sum them over the different elements and integrate them over the soil horizons. And then we obtain the total mass, which is lost by chemical weathering in the soil profile. So this gives us an idea of one position along the slope, but it's important to look at the hill slope topography. And so by integrating concepts of soil toposequences or soil catena, it is possible to look at the transport and the remobilization of material from eroding top positions towards depositional or convex positions. And we can see in this nice diagram, which was published by Wackett in 2018, that the redistribution of soil particles, colloids and solutes along the slope is largely a factor of geomorphic processes, but also soil hydrology, which is playing a role on the chemical weathering. We also see that the vegetation development and plant nutrient cycles can also be dependent on the slope position. So now let's have a look at the data. I will start with the data on the physical deformation. So in this graph, we can see that the physical deformation of the soil matrix is largely controlled by the organic carbon content in the soil horizon. So in the graph, we can see that for soil horizons which have an organic carbon content above 3%, that there is a significant and a positive relation between the organic carbon content and the dilatation of the soil matrix. So this points to the importance of the vegetation in supplying organic material to the soil matrix and by creating void space. This void space can then be used to transport solutes in the soil matrix and to enhance chemical weathering. So then if we look at the chemical depletion of the soils, so we see here on this graph the total mass loss. This is in kilograms per square meter. We see typically that these soils, they're highly depleted. Although these are post-glacial soils, we see that they are heavily depleted in monovalent and bivalent cations. And what is interesting to observe is that if we look at the topographic position, we see that the topography only plays a very marginal role on the total weathering extent that is observed. So the soil development and differences in soil development are only marginally significantly different between topographic positions. However, we see that the vegetation type plays a dominant role. And if we look at vegetation, we see that the vegetation type plays a significant role on the weathering extent of the soil matrix, even independent of the topographic position. We can see this in the diagram over here, where we see that forests, and typically these polylepis forests as we observe them here, they have significantly higher total mass losses, about 20% higher than cushion-forming plants and the grasslands. So these data show us that there is a very important covariation of the vegetation type with soil development, and with soil development in this type of landscapes. And this can point to two things. This can point to the fact that the biota and the vegetation play an important role in conditioning and in weathering the rock to soil material, and by changing also the soil water fluxes. However, it can also indicate that there might be abiotic factors which are controlling the vegetation development and which are also controlling differences in the soil weathering. So in short, this covariation between vegetation, topography, and landscape evolution is still poorly understood. And I think to make a major advancement here, it's important to collect data both on the biotic and the abiotic part, and to integrate different spatial and temporal scales. So now let's move a bit down. So we have been looking at the paramo or the pajonal vegetation zone. Now let's have a look at the mountain forest vegetation zone. So maybe you can see already from this picture, there is not much left of the mountain forest. So most of the area is entirely transformed into an anthropogenic landscape. So the mountain forest zone is the area where we find the big cities, where Bogota, Medellin, Quito, Cajamarca are located. It's the area where we observe agricultural fields, pasture, and urban and rural centers. And we will have a look now how this affects, how this human transformation of the landscape affects Earth surface processes. Now, if we start to zoom in and we look at small plots where we can measure runoff generation mechanism by using sprinkler experiments, we can see that the vegetation and the land use place a priori control on the runoff generation mechanism in these areas. And we can see this in this graph over here. So these are accumulative runoff coefficients. So it gives us the percentage of the rainfall which is simulated on the plot, which is generating runoff. And what we can see is that areas like wastelands and abundant lands, they generate a lot of runoff due to Hortonian overland flow. And so we can see that these areas generate about half of the rainfall which is generated on these plots is also leaving the plot by runoff mechanisms. And so, in contrary to what is often expected, agricultural fields and pastures generally generate much less runoff because of their relatively good vegetation cover. So now, when we look at the sediment production at the catchment scale, so relatively small catchments in the order of a few square kilometers. So when we look at these small catchments, we see the following. In this graph, you can see the sediment yield. So this is the amount of sediment which is leaving the catchment at its outlet. So the amount of sediment which is measured over here. And in this graph, this is plotted as a function of vegetation cover. And what we can clearly see from this graph is that the vegetation cover again exerts a primary control on the sediment yield leaving these catchments, also pointing to the fact, to the importance of anthropogenic disturbances in the vegetation to sediment yield generation. However, one can say, okay, but we are in mountain environment, so it's important to take into account natural processes, because even if the area would be completely forested, we still measure a sediment yield. And this is correct, and that's also why we started to work with isotopes. And so we use cosmogenic radionuclides in order to have geological or natural erosion rates. And so they give us a kind of a long-term benchmark. So this is what we measure in natural systems. And so we can see this on this plot here in the open dots. And so on the open dots, we see the natural benchmark. The black dots give us the anthropogenic signal. And so here again, we clearly see if we change the vegetation cover, we exponentially increase the sediment yield by almost 100 times. So these are data which were collected on plots and on small catchments. So now the question is, can we extrapolate this to larger fluvial systems if we want to understand, for example, the impact of anthropogenic disturbances in the Andes on the sediment export to the Amazon? This is an important question. And so the issue of extrapolating data on these smaller scales to larger fluvial systems is a complicated issue. And we see this already in this graph, which was published by Van Mark in 2015, where he compiled data on sediment yield. And so in his graph, you can see on the y-axis the human impact factor, which he calculated by rationing the measured sediment yield by the sediment yield of corresponding pristine catchments. And so you can see in his graph, where he plots this human impact factor as a function of the drainage area, you can see that the catchments which are relatively small, so till 10 to 100 square kilometers, the human impact factor is clear, and we have an acceleration of the sediment yield. However, if we look for these larger systems, it seems that the anthropogenic signal gets lost. So what is happening now for these larger fluvial systems? So one of the issues that might be important to look at in more detail is the sediment cascade. And so there might be a very important disconnectivity in these larger fluvial systems, which prevent us from upscaling directly the observations which are made at the plot and the small catchment scales to these large fluvial systems. Because typically what we are looking at is the process of sediment production on hill slopes and in small catchments, where we clearly see the effect of anthropogenic and climate change disturbances. However, their effect on the sediment transport and their effect on sediment deposition, either in temporary stores or in permanent sinks, is not yet well established. And therefore, this graph, which was published by Flareups already in 2012, on the spatial and temporal disconnectivity in large catchments, provides us with an interesting framework. And so in this study, she has shown that within a catchment, only a very small part of the larger fluvial system is connected to the river. And so we can see this in this graph over here, where the gray area is the area which is contributing sediment to the fluvial system. And so she has indicated that the area which is geomorphically effective is also increasing with the magnitude of the event. And we can see this over here. So if we look at larger magnitude geomorphic events, a larger portion of the catchments become connected and contribute sediments to the fluvial system. And so the effect of the effective timescale, which is the timescale over which the whole catchments become connected and contribute sediment to the fluvial system, is important to take into account when we analyze the propagation of disturbance signals in these large systems. And an important contribution was made by James Pisuto in 2017. And this is a numerical simulation in which he shows, based on sediment budget data, that the travel time of sediment in fluvial systems can be very long. And so he made a comparison in the travel time of sediment in fluvial reaches of 25 kilometers and 1,000 kilometers. And so what you can see from this graph is that if we look at very small fluvial systems, most of the sediment flushes through quite quickly. And this is also when you would expect that the anthropogenic and the land use signal is propagated quickly in the system. However, if we look at these larger fluvial systems, reach lengths of 1,000 kilometers or more, the median travel time becomes very long. And in these simulations, he has showed that this is around 2.5 million of years. And so this important storage of sediment in these larger fluvial systems might play a very important role in the slowdown of the propagation of anthropogenic signals downstream. A second issue which is of importance is also the amplification of the signal by anthropogenic disturbances. And so the sensitivity of mountain areas to these anthropogenic disturbances might be highly dependent on the magnitude of the background signal. And what I'm referring to is the following. So when we are doing landslide studies in these mountain areas, like the one in the tropical Andes, we see that the changes in landslide magnitude frequency distributions, as you can see them here in this graph, they are highly shifted when we have anthropogenic land use. And this is particularly the case if the denudation rates are relatively low. If we go to areas where the background denudation rate, because of active uplift, is much higher, we see that the effect of these anthropogenic disturbances to the signal is much lower. And so my main point is here that this anthropogenic amplification of the Earth's surface processes might also depend on the magnitude of the background signal. So to conclude, I hope I took you to the fascinating environment of the tropical Andes, where we see very strong gradients in climate, geology, topography, vegetation, but also anthropogenic land use. And it's an excellent environment to study spatial and temporal dynamics in Earth surface processes. We have seen that the upper part of the Andes Mountains, where we have the Pajonal or the Páramo vegetation zone, it's largely affected by climate change. And these climate change signals might have important effect on the coevolution of vegetation, soil, landscapes, and also on the geochemistry and nutrient cycles that we have in these Andean rivers. If we go further downslope, we enter in the part of the landscape which is heavily affected by anthropogenic disturbances. There we have data and studies have shown that the anthropogenic acceleration of sediment production and erosion is very strong at the small catchment scale and the plot scale. However, if we want to take these observations and these measurements to larger fluvial systems in order to understand changes in the geochemistry or in the contribution of sediments to the Amazon basin, for example, we really need to have much more progress in understanding travel times of sediment in these larger fluvial systems and to see how these anthropogenic disturbance signals propagate downstream. Okay, with this, I would like to thank you for your attention. I'm happy to take some questions.
Thank you very much, Veerle. Are there any questions?
Hi, thanks for the wonderful talk. I was wondering, in Armando's study, where you looked at these different vegetation types and the response of chemical weathering, was the point that the climate had changed and therefore vegetation, or if not, how did you make sure that the vegetation was there for longer? Because you said the vegetation influences the chemical weathering. So, thanks.
Yep. Yeah, I think this is important in a follow-up study. So at the moment, what we mainly took into account is the current vegetation cover. There are data from pollen studies from a nearby lake, which shows that in this area, so the Pajonal, vegetation has remained constant. So what I was making allusion to the climate change in the Pajonal vegetation is the upper limit of the vegetation which is going up. So the upper limit of the Pajonal, and we also see the downslope limit of the Pajonal. So we mainly expand the range of the Pajonal vegetation. So this study case is in the center of the Pajonal vegetation zone. So it's important to look also and to compare with the pollen data to make sure and to be to look at changes in the vegetation over the long term and how they affected chemical weathering. And I think this will be part of a follow-up study.
Any other questions or comments? Sure.
What's the rate of soil generation in the high Andes compared with places like the Congo Basin, where everything drains internally?
Yeah, that's a very, very large question. Okay, thank you for the question. What is surprising from the data that we have on the high Andes is that these soil forming rates, these soil development rates, they are very high. And so we are in a cool environment. It's humid most of the time of the year. And also soils are saturated during part of the year. And so we were surprised to measure this kind of mass losses as we observed them today. Because I mentioned, so the soils, they are post-glacial. And so we have at the moment, there is about 60 to 70 centimeters of soil on top of the volcanic parent material. So we think that the vegetation development plays a very important role. And it's probably because we have the vegetation which develops, we have incorporation of the organic material in the soil. We have these humic acids which are rapidly weathering the volcanic material. So it's possible that the weathering rates which we measure in these high Andean environments, they are higher than the weathering rates that we measure currently in the Congo Basin. Okay.
Okay, thank you again, Veerle. And we will now move on to the last speaker in this session. So Shalal Senghor is professor at the Istanbul Technical University and a world-renowned specialist in the tectonics of Asia. He obtained his PhD from the State University of New York in Albany in 1982. He has been a guest professor at the universities of Oxford, Caltech, at the Collège de France, amongst others. He is a member of the Turkish, US, and Russian Academy of Sciences, of the Academia Europaea, and the Leopoldina Academy of Sciences. He has obtained, among others, the Bixby Medal of the Geological Society of London, the Gustav Steinmann Medal of the German Geologische Verein, and the Arthur Holmes Medal of the European Geosciences Union. We have actually invited Shalal for another reason, and that is that he also possesses what is probably the largest private library on geology and its history in the world, containing more than 30,000 volumes. It includes, amongst others, I've been told, a complete original volume of The Cosmos by Alexander von Humboldt. And Shalal has an encyclopedic knowledge of the history of geology, and therefore we asked him to provide sort of an historical outlook on Alexander von Humboldt's influence on modern science. So Shalal.
Well, ladies and gentlemen, we're going to be talking about a very great man. Alexander von Humboldt's name, as you will see, is usually considered equivalent to a genius. And this is what we all learn at school, in universities, and also in private conversations in areas where such things are talked about. Here is the man, Alexander von Humboldt as youth, Alexander von Humboldt in his old age. That's a beautiful daguerreotype, actually, that gives us a real image of the man without the artist in between. He lived to 90 years of age, which is quite respectable. This is where he didn't live. This is where he was born, raised, but then he was bitten by the travel bug. He traveled throughout the world, particularly South America and Asia. But his brother's family still lives here. It's the Heinz family. And on Wednesdays in Tegel, near Berlin, you can still go and visit it. I have visited it several times, and I think the last time was with Taylor, didn't we, Taylor? That was the last visit I paid to Tegel. This is in the grounds of the Tegel mansion, and that's where the Humboldt family members are buried. And that's where Alexander is buried, and you can see at the bottom of that central column, here's Friedrich Heinrich Alexander von Humboldt. He outlived almost everybody in the family of his generation. He was a very famous man. Now, however, we come to somebody's assessment of Humboldt. which is really interesting. This is Albert Einstein talking to Alexander Moskovsky. Alexander Moskovsky was an author, satirist, and all that. You know, he was he interviewed Einstein, and during the interview, he said, "Well, Einstein, you must have a Valhalla of geniuses in science." And he said, of course, you know, he counted a few, and he said, of course, Alexander von Humboldt. Surprising response. Beiläufig möchte ich bemerken, wenn eben zuvor die beiden Humboldt genannt wurden, so möchte ich wenigstens Alexander von Humboldt nicht in Genies beizählen. He says, when you mention the Humboldts, at least Alexander, he says, I don't consider a genius. And of course, Moskovsky was taken aback. He was shocked. He says, but why? And Einstein goes on, nun muss man sich vorhalten, dass Humboldt für uns heutige, wenn wir den Blick auf die großen Erkenner richten, kaum noch in Betracht kommt. He says, when today, those of us who live today, when we look back to the great discoverers, he says, we hardly think of Alexander von Humboldt. This is not so exalted a character. I mean, Ré de Moran was a complete nut. But he published some kritische Beleuchtung on Alexander von Humboldts Kosmos. But that's very interesting. He says, diese Wahrheiten werden von den Verfassern des Kosmos keineswegs bestritten. These Wahrheiten means that you should make a lot of observations, collect data. Aber begnügt sich damit, sie durchscheinen zu lassen, ohne dass es jedoch wagt, weiter auf die Erforschung jenes höchsten Gesetzes einzugehen, das ja selbst ohne seine Hypothese aufzustellen. He says Humboldt collected all that data, but he says he did not come up with one great hypothesis explaining the cosmos. So that's a little bit like Einstein's. Finally, a man who admired Humboldt. Charles Darwin writes to Joseph Hooker, I believe that you're fully right in calling Humboldt the greatest scientific traveler who ever lived. His geology is funny stuff. But that merely means that he was not in advance of his age. I should say he was wonderful, more for his near approach to omniscience than for originality. Whether or not his position as a scientific man is as eminent as we think, you might truly call him the parent of a grand progeny of scientific travelers who, taken together, have done much for science. Now, these are the sort of things we're not used to emphasizing about Humboldt. And what I would like to do in this talk is to argue that despite all these fairly damning remarks, Humboldt was a great man. And these three gentlemen, and this list includes two geniuses like Einstein and Darwin, these people really didn't understand what Humboldt was doing. And I will then emphasize that it is still a problem today that we have this dichotomy between people who, like the previous speaker, have collected a huge amount of data and gave us a wonderful understanding of what was going on in a part of the world that will help us understand how the planet's surface as a whole behaves, versus those who start with first principles, sit there in their offices in front of their computers, generate models. This dichotomy exists today. Now, this is the man's fame. I mean, look, this is the Museum für Naturkunde in Berlin. You see Alexander von Humboldt way on top. And when you go in there, this is the samples that he brought back from his travels. His first travel was to South America. As you can see, he started in La Coruña, then Santa Cruz, came down, and he just touched the edge of the Amazon Orinoco rainforest, where he discovered the Cacicare, which is the channel that connects the Orinoco with the Amazon. And people had been discussing in those days whether such a channel actually existed. And then he went back to Cuba, came back, went down the Andes, then went to Mexico, crossed Mexico, back to Cuba, and then he went to the United States to meet Thomas Jefferson, where he was given a very warm welcome by Jefferson from one savant to another. During these travels, Humboldt assembled an enormous database under exceptionally difficult conditions. Here he is with Aimé Bonpland sitting in the tropical forest. Look at all of their instruments are there. They managed not to break them, which is really amazing. Here he is again in the Amazonian rail forest. This is from a colored woodcut. Ladies and gentlemen, these are the results of one expedition. These are the results, this is the famous Relation Historique of these South American travels. And in here you find botany, zoology, geology, meteorology, geography. Humboldt collected a huge amount of data. Aimé Bonpland helped him with botany, naturally, and here he is, Aimé Bonpland. Here is an example of his notebook. He filled out these notebooks with very careful observations, and he deposited his notebooks in the relevant institutions. He didn't keep them. He put them where everybody could see them. Now, in the previous talk, you have seen that Humboldt also studied the distribution of plants on mountains. Here's a beautiful view of Chimborazo. It's seen from the Tapia Plateau, from the southeast. And on that, as they climbed, as everywhere else, they collected plants. And these plants gave them the idea of the distribution of plants with elevation. And they said, oh, how interesting. This is like the distribution from the equator to the poles. Now, this observation had already been made by Tournefort. But it was Humboldt that really clinched it and told everybody that climate and the atmosphere, the density of the atmosphere, very greatly affect distribution of plants. When he went to Mexico, he studied the geology. But he didn't stop there, because don't forget, in those days, Mexico, or New Spain, it was still a viceroyalty of Spain, it occupied about half of the United States today. Mexico was huge. So Humboldt got into the archives in Mexico and made the first usable topographic map of North America. And you'd be surprised to know that until the Gunnison survey in 1848, this was the best map. And it was copied and plagiarized by a number of Americans, not Zebulon Pike. Zebulon Pike did not plagiarize it, contrary to what Humboldt believed, but Aaron Burr and people like that, they actually plagiarized this map for their own political ends. Notice that here, von Humboldt not only drew the Sierras, but also the mesas, the flat-lying, high areas. And he noticed that this whole area was a little bit anomalously high. In Mexico, he left a tremendous reputation. Mexicans still love him, and justifiably so. And here is his great statue in Mexico City. Humboldt came back to Europe while he was working on the results of his studies, which was included geology. His great friend, Baron Georges Cuvier, published his famous, first the ossements fossiles, and then la géographie minéralogique d'environ de Paris with Alexandre Brongniart. And Cuvier said, every layer has its own characteristic fossils. And he explained why that was so. Because he said there are catastrophes and the evolution of the biosphere. He didn't have that word, but the evolution of living beings, he said, is unidirectional. It doesn't go back. And therefore, you can use it to date, at least to correlate, not to date, but to correlate sedimentary strata. I mean, William Smith did a similar thing, but Cuvier really erected the theory. I mean, without Cuvier, we wouldn't have biostratigraphy today. But Humboldt said, wait. He said, you're saying that every layer contains its own fossils and that it could be correlated worldwide. He said, not so fast. Look at the Earth today, he said. We have the polar regions, the temperate regions, and the equatorial regions. Well, you're not going to find a single species common to the equatorial regions and the polar regions. So how are you going to correlate them? He said, you're ignoring geography. You're ignoring paleogeography. Ladies and gentlemen, this is a criticism still valid today for biogeography. This is from his famous book, Essai géognostique sur le gisement des roches dans les deux hémisphères. Humboldt, this is the famous Orizaba in Central America. He visited almost every one of these bloody volcanoes. He looked at their rocks, and what is really surprising, that when he was leaving South America, he was still a Neptunist. He still thought it was the coals, etc., burning on the ground, creating the volcanoes. He was so much under the spell of his teacher in Freiberg, Abraham Gottlob Werner. He brought a friend from South America. This is Jakob. That was his pet. Well, unfortunately, when Jakob died, Humboldt couldn't part with it. So he said, why don't we taxidermy it and stuff it and preserve it? When they were taxidermying it, they realized that good old Jakob was a female. Humboldt had no idea all these years that Jakob was a female parrot. After he came to Europe, he talked to his old schoolmate, rather university colleague, Leopold von Buch. And Leopold von Buch said, you know, Alexander, he said, I changed my mind about volcanoes. He said, they are not things burning underground. He says, they come way down from magma. And he said, unfortunately, our dear teacher, Werner, was wrong. Humboldt then, having talked to Leopold von Buch, he went back to his own data and he said, now let us look at the volcanoes from a different viewpoint, from a volcanist viewpoint. And this is the first publication that shows Humboldt as a volcanist. This is über den Bau und die Wirkungsart der Vulkane in verschiedenen Erdstrichen. Now, here I want to emphasize that he was comparing volcanoes with volcanoes in Europe, with volcanoes in South America, with volcanoes in Central America. Humboldt laid great stress on doing comparative earth science. He did not confine his attention to a single place, but he compared the whole globe. Then, in 1827, he started giving some lectures in Berlin. They were so popular that the university said, well, we can't accommodate all these people. So he went to the Singakademie, to a concert hall. That's where he lectured. And these are the Vorlesungen über physikalische Geographie von Alexander von Humboldt. Now you're looking at what's been called a Mitschrift. That means that the student is sitting and writing down the notes. Now, there are 4 copies known of this kind of notes from Humboldt's lectures. 3 of them are in the German National Library, and the copy that you're looking at is in my library. But the German National Library asked me whether they could copy that. I said, with the greatest pleasure. And they said, well, they will, pay for the expenses and all that. I said, no. I said, we'll provide them free of charge. And there's a lady sitting back there, Nailan Lom. Dr. Lom sat down and copied all of that for the German National Library. And now you have direct access to that copy too. This was published later both early in the 20th century and also recently for the 250th birthday of, for the 200th anniversary of the return of Humboldt from the South American trip. It was published also by Insel Verlag. Then Humboldt came back, lived in Paris, but then the king said, enough of being a Frenchman, don't forget you're a German, come back to Berlin. Humboldt didn't really like that. I mean, he thought Berlin was a bit of a backwater. He wanted to live in Paris. But if the king was calling and he was out of money, so he had to go to Berlin. But as soon as he was in Berlin, he was giving all these lectures, etc., he got a letter from Baron Cancrin in Russia. Cancrin was a German, actually, but he was the Russian finance minister. He said, Baron, we are very curious in Russia whether platinum could be a basis for the ruble, for our money. And he said, we want you to look at the recent discoveries in the Urals. Would you please come, all expenses paid? And Humboldt always wanted to see Asia. He wrote back, he said, my dear Baron, he said, I will come, but if you allow me to go all the way to Central Asia. And Baron von Cancrin said, oh, no problem. He said, certainly, we'll pay all the expenses. Don't worry about that. And he said, we'll give you an escort and all that. So this is the trip, ladies and gentlemen, undertaken by a 60-year-old man in the beginning of the 19th century, 1829. And these 2 young men accompanied him, Gustav Rose, great mineralogist, and Christian Gottfried Ehrenberg, one of the creators of micropaleontology and microzoology. 2 books came out of that from Humboldt's pen. The earlier one, the Fragment de géologie et de climatologie asiatique, and the second one is Asie centrale, 1843, Recherche sur le gène des montagnes de climatologie comparée. Look at the conditions under which they were traveling. Think of those immense distances. The 60-year-old man sitting in, the West American cowboy style, post wagons. And the results, he kept notes wherever he went. This is a historical page where Humboldt in Buchtarma, along the Irtisch, he saw granites lying over the schists. Well, that didn't agree with what Werner had told him. He said, is this the granite had flowed over it, or what? What he didn't know that already an Austrian geologist, Franz Benedikt Hermann, in 1804 had correctly identified it as a thrust fault. And as far as I know, it's the first thrust fault ever identified in the world. Along Buchtarma, I was very lucky that I actually went to see it. This is Humboldt's tectonic map of Central Asia. And you can see that he had the Altai, and then the Tian Shan, then the Kwenlun here, and finally curved the Himalaya. He said these successive mountain ranges characterized the orography of Asia. He came back to St. Petersburg, and they said, well, yeah, do you mind giving a lecture in front of the Tsar? I said, oh, yeah, sure, it was a great pleasure. This lecture has nothing to do with his trip. Here, Humboldt urged the Tsar to set up magnetic observatories throughout Asia, throughout the domains of the Russian Empire. He said, we need that global data for the behavior of the magnetic field. And the Tsar did it. This was another enormous contribution of Humboldt's, that he got going the global magnetic observations. Towards the end of his life, he wrote Cosmos, couldn't finish it. This is a wonderful book. I recommend all of you to read it. That's the original you see on top. The bottom is the Eichhorn, the Insel Verlag had published this, Alexander von Humboldt's Cosmos. This is in one volume, all 5. I would wholeheartedly recommend you read it, even today, even though it's completely out of date. It's wonderful reading, and it'll give you a joy of doing natural science. This is the sad last page of Cosmos. This is where his pen fell off his hand. He couldn't finish it. And here it is. The angel of death is inviting the Baron to the grave before he could finish his Cosmos. And you can see the Cosmos on top. The angel of death is carrying it. This is the Atlas by Bromme, not authorized, but still a useful accompaniment to Cosmos. Now, what is left for of Humboldt's way of doing? Einstein belittled it. He said, what did he discover? Well, he was full of shit, Einstein was. Because now I'm going to show you a series of pictures of people who spent their lives collecting data and thinking about data. We start with Maurice Ewing. He was a good Texan. After the war, he went to the US Navy. He said, look, boys, you've got all these wonderful instruments, but you're not going to use them anymore. May we use them? And the Navy said, sure. Lamont, in those days, only Lamont, Geological Observatory with Vima, they put all these instruments on that luxury yacht and started measuring everything in the world's oceans. I mean, Maurice Ewing was a physicist. He was not the most imaginative scientist. He said, you go out, for whatever reason you're going out, you measure everything. Gravity, magnetics, absolutely everything. He said, you don't come back without having measured everything and taking cause. This is Harry Hammond Hess. Here he is in his admiral's uniform. Harry Hess was looking for Japanese submarines and mapping the seafloor. But the US Navy said, look, do not leave your sonar on all the time, because if you can hear the blip, so can the Japanese. So he said, you'll endanger yourself, you'll endanger your vessel and your people. So he said, turn it off. He said, yes, sir. He didn't. He left it on. And he mapped the whole of the Central and Western Pacific. And he came up with this funny map with all sorts of volcanic-like structures. The tops had been planed off. He said, what the hell are they? You know, he realized they were volcanoes, but at 4,000 meters depth, why did they have a flat top? He said the only explanation, they must have been higher and subsided. And from there, he got the idea of seafloor spreading. Now, that sort of data had been abundantly present in Lamont after the war. So when they heard Harry Hess's discovery, they said, let's look at the world's oceans. They did. To their amazement, they found this mid-ocean ridge. Only because Maurice Ewing said, map bloody everything. You know, even if you don't understand it, map it. So we got with that. Then, good old Tuzo, he noticed that these ridges were offset. But he said, if Hess is right, then this offset does not reflect the real offset. The real offset is the opposite, has to be the opposite. And he published that memorable paper, A New Class of Faults and Their Bearing on Continental Drift, 1965, Nature. Read that paper. That paper is the first paper on plate tectonics. It has the word plates, it has all three boundaries, it has the rules in it. So Tuzo Wilson single-handedly came up with a theory of plate tectonics on the basis of this huge amount of data that had been gathered earlier. But afterwards, Lynn Sykes from Lamont, he said, oh, that's an interesting idea, the Wilsons. He said, but we can check it. We have the pop plane solutions. We have the data. He went, looked at it, he said, by God, he's right. Dan Mackenzie, he said, if Wilson is right, then the slip on the San Andreas must be absorbed by the Aleutian Trench. They too looked at the seismology, the fault plane solutions, but Dan was very clever, he said, never mind these PT axes, let us look at the slip. When he looked at the slip, he realized the slip was the same everywhere, exactly as Tuzo had predicted. Fred Vine and Drum Matthews. Fred, as a graduate student, said, oh, this is very interesting. If seafloor is really spreading, the basalt is coming, if the magnetic field keeps changing, then this has to record that. And we have to have a sort of striped seafloor. And by God, it was right. Jason Morgan, he said, if Tuzo's idea is right, that has to work on a sphere. And he published that memorable paper showing that it really did work. Xavier Le Pichon, at the time, a postdoc in Lamont, he said, if this thing has been going on, the magnetic record must be on the ocean floor. So he gathered all the magnetic data that Lamont had collected for years. And he looked at it and he said, by God, this damn process has been going on at least since the Jurassic. So, ladies and gentlemen, we should ask the muse of the history of science. Andra moi enepe, Musa. Polit roponos malapolla. Does anybody recognize this? This is the opening line of Odysseus, where Homeros asks the muse, he says, tell me of that much-traveled man who defeated Troy. Who defeated Troy is not here, but he says, tell me of that much-traveled man. So we will ask the muse again to tell us about Alexander von Humboldt. And Humboldt is not a dilettante, as Einstein might have thought, but he really told us what modern science will be like, will observe. And the speaker before me very beautifully underlined that. We have to observe, we have to collect data, but that doesn't mean we have to stop thinking. We think as we collect data, we generate hypotheses. And the man who was born in this very city, Karl Popper, told us how this is usually done. You erect a hypothesis, you test it mercilessly. How do you test it? With observations. And Humboldt, when he presented the ideas of Élie de Beaumont, which was a completely deductive theory of orogeny, Humboldt said, well, that's really very clever, it's nice. And then he said, it's not for me. And he was right. It turned out to be complete rubbish. Humboldt said, let's have our hypotheses, but let's have our data. Let us observe. And today, when people say, oh, you know, we no longer need to map. You know, we have our computers, we can model things, we have our physics. If you go that way, you're going to hit your nose against the wall. Humboldt-style data gathering, especially good geological mapping, good botanical mapping, good zoological collections, they have to continue if we really want to understand not only this planet, but the others as well. I mean, I've worked on Mercury, I worked on Mars, and when we worked on Mercury, the people who poo-pooed geology, they had mapped 16 shortening structures. When we geologists went back, looked at it, there were 5,900 of them. So, once more. Andra moi enepe musa polytroponos malapolla. Thank you.
Thank you, Shalal.
Thank you.
And I suppose you're willing to take some questions, if there are any questions.
I'll repeat what I said the other day, what a gullible audience. Or they've been overawed by Humboldt. And that's a good reaction.
Okay.
Thank you.
One question.
There is a question.
Yes.
Oh, delighted.
Hello, Shalal. This was wonderful. I mean, I don't think I've heard a more exciting talk in this building or even before the EGU. I really want to pick up on these two opposing points of view. You know, clearly Einstein, who needs no further praise, but he was a snotty physicist in this, you know. I mean, if physics is great theories, and then you have experimentalists go and check, and you mentioned Karl Popper, you know. The truth, of course, is that nobody follows Popper in his work. You know, we don't disprove our...
We have our colleagues for that.
Yeah.
Or our colleagues make damn sure that we're wrong.
My point is that indeed in the geosciences, or whatever you want to call them, what we all do here, there is the opposite tendency, which is the Maurice Ewing tendency: collect data and run the ships, now run the big models, etc. And then you, the theoretician, explain to me what this is. The problem, of course, with that point of view is that there are always many explanations for the same data. And so there has to be a little bit of both, because really the Occam's razor or Poincaré's parsimony principle says, you know, it's simpler theories that ought to prevail, and not the ever more complicated models that are being devised to explain more and more of the greater and greater sets of data. Yeah. So I think, you know, there has to be a little bit of both, but we can talk more about it.
No, I mean, that is true. I pointed out that when you collect data, you have to continuously generate hypotheses and models, because if you don't, you get stuck. You know, you wouldn't know what to observe. You know, I mean, it's extremely important. You don't ask your students when you go to class, you say, take a pencil and start observing. The first question they will ask, what? You know, that what is answered by hypotheses, by pre-existing knowledge, or at least pre-existing thoughts that we think is knowledge, but we hope that our students will prove it all wrong. But it is extremely important to be aware of this, as you point out, two steps in science. You observe, you generate hypotheses to explain them, then you observe on the deductions of those hypotheses, then you suddenly hit on something that tells you that hypothesis was wrong. So you generate another one. and you start observing on the basis of that. But as you point out, of course, individuals don't do that. We are too egotistical. We think we are all right. Okay, but fortunately, we have our dear colleagues who are dying to tell us we're full of shit. And that is one thing I find grandiose in science. You know, we thank people who show that we've been wrong, because we learn something new. I mean, we're all in this business to learn and to understand. And we don't want to fool ourselves deep down. And when somebody says, look, you're full of it, then we say, oh, thank you. If we believe that. I mean, as a student, I have seen examples of that. When I was in Albany, you would walk up to John and Kevin, and you'd say, oh, this particular thing that you published is rubbish. They would say, oh, tell me why. And if you prevail, they would be delighted. I have witnessed it many times. And it was a precious lesson. And that's why John and Kevin are great people. Like Humboldt. Humboldt was wrong in most of his hypotheses. Doesn't make him a smaller scientist. He was a very great man. Thank you.
Thank you. Okay. So with those wise words, we can close this session, and I thank you all again for coming and attending, and wish you a happy end to your EGU this afternoon.